Like, should take someone else's up.
You're live. Here. I assume you want to share the SDR tab?
Yeah. Hi.
Yeah, someone pull it up on there and then see if it works.
Video.
Well, so that might be a weird sharing thing. I need to share the window.
So I'm gonna do the Chrome tab.
No, hold on.
See if you can share the PowerPoint on it.
Yeah, so I think what needs to happen is you need to go slideshow. And share this. What if I just share the screen?
Oh, it's showing the audio.
Does that work? Can you see us? Awesome, that is sick.
This live stream thing works, right?
I think it does now. Thank you.
What did it wasn't working before?
We had some trouble saying out, but now it's all good.
Yay!
Awesome. This is a really good question, All right. This does not work. It doesn't. No working. Hello. Good morning, everyone. We're going to get started here. If everybody could please scan the attendance QR code on the slide, and we'll register your attendance for this event. While you're filling that out, I do have a couple reminders. First of all, this is our system design review, our first major review day. I'll be going over agenda on the next slide, but do keep in mind that while you're up here presenting, that this event is live streamed and recorded and will be published online. We have this OWL meeting camera up here, so anybody who's up here will be recorded and visual on the live stream. So just keep that in mind. Also, for this design review, we'll be working through lunch, at least that's the plan right now. If it looks like at around noon we are running behind schedule, then we'll schedule on a lunch on the spot. But right now we're planning to end tentatively around 1 p.m., working right through lunch. Looking at an agenda for today, we're going to start with a high-level robot overview by our chief engineer. And then our fab operations lead is going to talk about a unique 2-robot proposal, something new this year that we're going to really strongly consider. And then we're going to move into each of the presentations by the respective sub-teams, starting with excavation, followed by deposition, drivetrain, power and hardware, software, and systems. Lastly, we'll finish with some business and concluding remarks by the president and the chief engineer. With that being said, I'm happy to see you all here this morning, and I'd like to invite Andrew May, our chief engineer, up to start with a high-level robot overview. You can use the mic if you'd like.
All right, hello everyone. My name is Andrew May, and I'm the chief engineer for Purdue Robotics. So I'm going to be giving a high-level robot overview of our currently planned system for this year. In terms of mass allocations, by going around the sub-teams, our current overall system mass is anticipated to be around 58 kilograms. The breakdown being drivetrain is going to be about 20 kilograms, excavation also being about 20 kilograms, deposition is about to be 13 kilograms, and then P&H and software is going to be somewhere around 5 kilograms total. In terms of design goals for this 2025 to 2026 season, as always, we're trying to reduce mass where possible. We're also wanting to increase our mining capacity as well as our regolith capacity. We're also again trying to improve traction with our wheels during traversal. Another goal is to improve assembly and maintenance efficiency, just so that way assembly and maintenance of various components and systems is a lot easier and quicker. We're also going to explore the new proposed 2-robot system and see where the possibilities lie with that. I'm also going to be talking about our technical performance measures, or TPMs. So basically, TPMs are derived from our robot system requirements, and they're created by the sub-team leads. And they will also be presented at all of our future review gates as well. In terms of what TPMs actually are, they're essentially a design threshold that components must be within. These are some of our specified technical performance objectives, so things that are kind of outlined within the guidebook and then our stakeholder requirements. For example, the robot shall be contained within a payload envelope measuring 1.5 meters in length times 0.75 meters width and 0.75 meters height, and that is mandatory. The robots shall also not exceed 1.75 meters in additional height or 2.5 meters above the surface of the regolith, which is also mandatory. Then the robot shall not weigh more than 80 kilograms. This includes any beacons or external parts that we're using for navigation. And additionally, a specific rule that we may be using this year is multiple robot systems are allowed. However, starting dimensions of the robot shall comply with the maximum volumetric dimensions and mass provided, as well as any other requirement that we have to follow for a normal robot. And then overall technical objectives that we're going for is the robot should minimize weight, the robot should minimize its part count, the robot should have fasteners in easily accessible locations, the robot should contain parts that are easily removable, disassemblable, or replaceable. The robot should contain components with low lead times as possible, just trying to make the assembly as quick as possible. The robot should also minimize power consumption, should incorporate dust-resistant features. The robot should be able to complete the mission autonomously. And the robot should use encrypted communications. And these are all kind of just competitive goals that we have. In terms of our actual specified technical performance measures, our upper limit for mass is 80 kilograms, with our threshold being 58 kilograms right now. Our average power is going to be measured in watts and an upper threshold of 250. Our upper limit for bandwidth usage is 4,000. The system length max stowed is going to be 1.5 meters as an upper bound. And then width and height are both going to be 0.75 meters. System height max extended is going to be 2.25 meters. Regular storage capacity, our aim is as a lower bound as minimum should be 10 liters. Our build period should be around 6 minutes. And then our instantaneous peak for power should be about 750 watts. And now I want to invite our FabOps lead to present the two robot proposal.
Excellent. So thank you, Andrew. My name is Alex Repikov, and I am this year's FabOps lead. I'm here to present a proposal for two different robots. A lot of the sub-teams already know about this, and the relevant ones, I believe, will be talking more about it in their specific sections. But I'm here to go and give a general overview of what the idea is and why we might or might not want to do it. General overview is that we have two robots. The first one will be the main robot, and this robot will go and mine regolith into its own deposition system, similar to ways we have done previously. We go and mine, we go and store it. What is different is that this robot will be always mining. It will never go and drive over to the deposition zone. It will just collect its regolith and hold on to it until the mini robot can come. And the mini robot's only job is to go and shuttle regolith between the main robot and the deposition area. And its only job is to do that as fast and efficiently as possible. So to summarize, the main robot will always be mining. The main robot will always be moving, which means we'll be able to get more points because the main robot never has to stop mining to go and actually deposit. Now we have charts. Thank you to John from Drivetrain because for the chart, it is very useful. So this chart is the curved lines are the amount of points that one robot would score for a given size of excavation deposition, and the straight line is two robots. For properly sized systems, because excavation deposition need to be sized relative to each other, roughly, two robots will score somewhere between 1.25 points, especially around the numbers that we are aiming for. And this is with quite a lot of assumptions against two robot. This is assuming that only 80% of the regolith gets transferred correctly and 20% falls off the robot or something else in between the two robots. Looking at this chart, we are likely going to be limited by deposition volume. For any excavation speeds that we have that are especially going off of last year, our deposition volume needs to be quite a bit bigger than it was in previous years in order to make the most of our points. Some more on the system sizing. On these charts, the robot capacity in deposition is on the horizontal, and the top chart is on about mining speed, and the bottom chart is on drive time. So two robots can score up to 1.7 times as many as one robot in optimal situations where everything works out. Our current estimated values, which is pulled from these slides, fall at around 1.2 times. And we can improve that by either increasing deposition volume or drive speed, which are things that we might want to consider doing anyways. And the lines are at the current estimated volumes and speeds and all of that. And just a high-level comparison, the pros is we'll score more points. We'll score between 1.2 and probably 1.5 times as many mining points, which is always good. There will be additional redundancy. If the mini robot can completely break down and the main robot can then transition from being a purely mining robot to a mining and deposition robot, the same as it would be in a single robot system. So there is some extra redundancy built into building a second robot. It is also unique. To my knowledge, no one in Lunobotics, us or any other team, has ever attempted successfully a two-robot system. And that would be, for lack of a better word, really cool if we were able to pull that off. Some cons, it would be, well, just more work. There would need to be additional design work. There would be additional mechanical complexity because there's two robots. There would be additional manufacturing. There would be additional software work. And perhaps the most important one, we've never built a mini robot. We don't know all the troubles that can go into it in the same way we know all the trouble that can go into building a main robot, because we have a lot of experience. We've built several of them. We have not built a mini robot. That is all that I have. Are there any questions? Cons?
Can you provide some clarification as to why we're only considering it this year and haven't in the past?
Yes. So in past years, the layout of the field was that the robot starts in the starting zone, it then goes through an obstacle zone, and then reaches the excavation zone. And the excavation zone and the deposition zone are right next to each other, which means that the distance to go between the excavation and deposition, where you go and dig and where you dump, takes maybe a couple seconds. This meant that a two-robot system wouldn't actually have sped up the process that much because the main robot didn't have to drive that far. Now, the robot starts in the excavation zone and then has to drive through the obstacle zone to the dump zone, which means that now the drive times are now much longer. Our estimated drive times are somewhere in the range of 30 to 60 seconds, depending on factors such as number of rocks and exact speed of the robots. So drive time becomes much more of a factor this year, which is why offloading that to a separate robot becomes more important. Sophia.
How would the volume of the two deposition systems compare? Would the small robot be hold half the volume that the larger robot's deposition can, or would it be smarter to have? Because that would be what your calculations were based off of, I'm assuming.
No, they were based off of off of the same size.
So they both have the same deposition?
Yes, yeah.
And so how would that reduce the size of our big robot?
I'm not sure if it would reduce the size of our big robot by all that much, because again, the traversal time is pretty long. So we want to go and mine as much as possible on every trip, because if we're spending a minute going and getting back and forth, we don't want to go and do that for a handful of regolith.
Yes. So did you just take the previous dimensions of our robot and then filled it to the upper limit and made that the dimensions of the small robot?
I don't know how the sizing was done.
Because if we just had two deposition systems, 6 times is probably way over.
For drive through, I talked more about how the sizing of the mini robot can fit into the big robot, because we don't use the full length sizing available to us for the main robot. So we could leave the main robot as its current size and still have space for a big robot that's pretty decently sized.
And I'm assuming the deposition would be smaller.
Peter has more.
So my comment on this is that it sort of doesn't make sense if the two robot, the mini robot has to have either the same size deposition or larger for the system to make sense at all.
Yeah.
Because the excavation robot basically needs to be able to fully fill up the small robot. And so if the small robot can't hold as much as the main robot, then the main robot fills up its system, and fills up its system fully, and then dumps a portion of it, and then as the small robot goes to deposit, it fills up the system, and now it can't hold anymore, and it has to stop mining.
I agree. That makes a lot more sense to me.
Yes. Yes,
So
Peter. Oh, sorry.
That throws off the capital a little bit for the point maximizing.
I am not sure it does. All these would assume that they had the same deposition volume. So if the main robot had a volume of 20 liters, so does the small robot. If the main robot has a very large volume of 40 liters, so does the small robot.
Okay. Would you buy 2 LiDARs, or how would that look for autonomy?
I'm not going to speak for software, but my understanding is that we have a lot of depth cameras we can use. Each robot would need to have at least some cameras on it, because otherwise it needs to know where it is within the field. I'm not sure what the plan is for LiDARs and stuff, but I expect you will hear a lot more from software. Unless, Ankur, you want to chime in now, or are you going to?
We'll talk about it.
Okay. Yeah.
As far as automation goes, as well as the driver control period, how are we gonna divvy up how long the driver is able to operate the robot and then how long it's automated? Or will we just automate both of them for the entire time?
We will be. Our goal is to automate both of them for the entire time, and I'll let software talk more on this. But we get more points if we are completely autonomous. As in, basically, the run starts. We say, "All right, go," and then we sit back for the next either 15 or 30 minutes, and then at the very end we say, "All right, now you can stop." So that is what we are aiming for, and I believe this is possible to automate. Software can talk more about this in our section. Peter.
A couple of questions. The first question is, you mentioned the additional redundancy in that if the mini robot breaks down, we can still transition back to a single robot station. Is there a concern that the mini robot could very easily break down in such a location as to block off the deposition zones from a convenient path and make it more difficult to actually complete the function progressively?
I think that is a possibility. However, my counter to that is that, well, if a robot breaks down, that is already oh God, things are already going really terribly. So having any way to recover from that at all, even if it's not the most optimal route, is, I think, better than not having that option. So yes, to answer your question, the robot could break down in a very inconvenient spot and we have to go, instead of saying, well, there's a nice convenient route here, but now we have to go around. But before we didn't even have the option of going around, before we had we were told, hey, well, I guess the robot's stuck, I guess we can't do anything. Now we can say, well, hold on, we can still work around this.
And then my second question is less of a question and more of an observation that
Sure.
we will need to modify the manual control scheme to implement probably 2 controllers or some method of switching. So that in the event that our autonomy system fails, we would have to have 2 separate people we'd have to have 2 separate people probably controlling each of the robots.
Yes, that is correct. I've talked about this a little bit with software already, and yes, we do think that the 2 controllers and 2 people is probably the best way to go around that. I'm not super concerned about that because we do have 3 people in the control room, and that still leaves 1 person to go and interface with judges, and then 2 people to go and be in charge of manual driving, should it ever come to that. Kyle.
Given your single robot numbers end up being, well, your 2 robot numbers end up being 1.2 times your 2 robot system, have you considered, instead of having a dedicated mini bot, instead of having 2 of the exact same robot that has a total system mass that is the same as the big robot and mini bot that you calculate, but should in theory get you double the single robot system points, like the same mass as your 2 robot system points. And that would provide the redundancy that you're also talking about in case a robot fails.
The main reasons why that isn't why this isn't that option are because if we end up doubling the robot system mass, even if we mine double the amount of regular, that's not actually enough. So if we take two robots, we'll actually score about the same number of points as 1 robot, because for those unaware of how the scoring system works, it is the amount of regular that you mine divided by your robot mass.
That's why I specified same mass as your current proposed 2-system robot.
Yes. That would, another thing is, yeah, Ankur, you had something?
If we could make a robot that can do everything with half the mass, we should just take that 1 robot and not have the second one, because that would just be a better robot overall. Unfortunately, I think excavation is probably the heaviest subsystem, and if we could make excavation significantly lighter, then it would be hard.
And
the only reason I mainly ask that is I know that in the spreadsheets, your mini bot mass is about 20 to 30 kilograms, and your full system mass is 50 to 55.
yes.
So if you end up making it so that you have 2 40-kilogram robots, does that perform better than a 50 and 30-kilogram robot?
I don't know. I haven't done those numbers. I will say that so I believe our current estimated system mass was 58 kilograms. Going from a 58 kilogram robot to a 40 kilogram robot is going to be hard for all sub-teams involved. That would involve drivetrain shaving 5 kilograms, excavation shaving 5 kilograms. That is a lot of effort, and I'm not sure that is possible without some serious compromises and or changes to systems that I don't know if we definitely haven't been planning for that. That's one of the main reasons, is that it would, having a robot that light would require some serious changes, and this one would require less drastic changes. And also, to Ankur's point, is that if we can make one robot, if we can make a robot that's 40 kilograms and mines very effectively, we should just take that one robot and not even bother with the second one because of the way that scoring works.
Which then that also couples with mining robot. How much of a benefit is your deposition robot if it is a fixed mass, if you're able to decrease your main system mass?
There are charts. I don't have them pulled up, but yeah, effectively decreasing mass makes the systems better. Decreasing the small robot mass makes 2 robot system scale much better. Decreasing main system mass makes single robot scale a little bit better. But from past years, I don't expect that our main robot is going to get significantly lighter. Maybe we'll hit that 50 kilogram mark from the 58 if we do some weight savings, but I don't expect we're going to get much lower than that.
Another thing that I'm now remembering, isn't there a hard limit on what the upper max of the system can be?
Yes, 80 kilograms.
Okay, because currently, I know that we're very close to that.
Yes, 78. So yes, that it will be somewhat of a concern once we flesh out the designs more and see what it ends up being. That means we can't like if we say we're going to have a 58 kilogram main robot, we can't end up with a 65 kilogram main robot, for instance. And if we say we're going to have a 20 kilogram small robot, we can't end up with a 30 kilogram small bot. But
I'm just very concerned about the sizing of your small robot because I don't see any meaningful reason why it wouldn't be effectively your main robot without the excavation system, which only loses you 20 kilograms.
it would have a slightly smaller drive base. And I am not the mechanical lead, so I'm not going to comment on the exact ways that it could be designed. But I think there are ways that we can design a robot that is like a lot of the space that is taken up by excavation doesn't need to be taken up, which means that not only is excavation not there, but so is all the supporting hardware, which will add up to more than 20 kilograms. And the robot will also have to be a little bit smaller. I believe deposition we'll talk about more, but I think it's going to be effectively a large bucket on wheels or on tracks or on whatever drivetrain tells us to do. Yes, Peter.
A similar point about weight concerns is that it occurs to me that with a cube robot solution, if we are dancing on the edge of the 80 kilogram limit, dust protection and being able to clean the robot off of dust in a sufficient way would suddenly perhaps become more important because historically the robot tends to pick up most of the mass as competition goes on from dust getting coating it and getting in places as far as you reach.
Yes.
And that would be more pronounced with more surface area, more nooks and crannies with cube robots, which could potentially lead to over the course of competition us actually exceeding the 80 kilogram limit. So it would be even more important to be able to clean out the robot.
I do think that is very important. I will say that I know in previous years we haven't been like gram chasing. Like I know Reggie still has a bunch of bolts in their wheels. That we could have taken those off and saved a little bit of weight, but we didn't because, well, we weren't that close and it ended up not mattering. If we're in a situation where we are, wow, our robot was 79.8 when we started, now it's 80.2 and we need to go and cut some weight, I do trust me to be able to go and say, we can go and remove some bolts, some excess bolts, remove some stuff like that. And that will require some more effort so that maybe 80 isn't our hard max for us. We say, hey, we want to stay under 78 kilograms. So we have space to get heavier as the year goes on, or something like that. Any other questions? Yeah.
This might not be the right area to ask this question.
Sure.
But you have 1,000 ways you can have a big robot and a mini robot that's doing the same thing at the same time. Why is it that we chose to have a main robot excavation and deposition and then a mini robot that just deposits instead of a main robot that just excavates and then shares the deposition system with the mini robot?
The main reason is that at some point, the mini robot will need to be over by the deposition system, over by the berm, which means it is not over by the main robot. And at that point, if the main robot is continuously mining, it needs a place to go and put the regolith and store it up until the mini robot comes back and is able to take more. That's why the main robot still has a deposition system. As to why this system over others, it was partially chosen because it is still a two-robot solution, which is still more work, but it minimizes the amount of work required as compared to a unique main robot and unique small robot, because the main robot is very similar to what we are doing this year. If we end up deciding in 4 weeks, we end up today saying, hey, we're going to do 2 robots, and then around PDR time we say, actually, 2 robots suck, we should never have done this. It's very easy for us to say, and then we're just going to not design the mini robot, focus on the main robot, and we still have that option. If we design a completely custom system that is different, we won't have that option. And also, the further we stray from the accepted stuff, the more time it'll take to design, which is why this design is very similar to our current stuff with something extra tacked onto the back. Kyle.
Just kind of a information
Sure.
thing. Have you run the numbers of if your mini bot fails, what does your point distribution look like? Good.
I have not. I mean, depending on when it fails, if it fails at minute 29 of KSC, probably not that different. If it fails before it even leaves the starting zone, it'll be worse because we just have a heavier system with nothing to gain from it. But then that also comes down to the fact of what if our main robot fails? What does our point distribution look like? And the answer is not good.
Yeah, but you have the admin weight. That's like why the question.
Yes. So, I do think that yes, depending on when it fails, it will stop providing its benefits at that point, and therefore we'll just end up with a heavier system. I think part of it is also we should do a lot of testing to make sure that it doesn't fail. But obviously that is not avoidable. Something can and will always have the possibility of going wrong. But and that's also the case with a single robot system is that, exemplified by our KSC run 2 last year, something can and will always go wrong in the worst ways. So.
Yeah, it's worth it to run those numbers though, to like see if like that severely like decreases.
Off the top of my head.
Might fall into a crater and not get out.
Yes, off the top of my head, if we're going with a 60 kilogram main robot and a 20 kilogram small robot, if it fails immediately before helping at all, then our point is going to be about 33% worse because our system weighs 33% more. So, and you can move that in depending on how much are we going to get halfway through? Are we going to get 3/4 of the way through? Or is it just going to fail outright miserably the first time we put it near regular? I don't know. I hope it doesn't. I hope we do a good job designing that doesn't fall into craters and do that. But obviously, it is hard to account for that. Anything else? All right, well, in that case, excavation.
Hi everybody, my name is Will Dans. I'm the excavation team lead for this year's excavation team, and we're going to start off going through our system requirements, go into each of the designs we considered for this year, and then finish off with the trade studies and where we'll be going for the rest of this year.
Hi guys. Okay, so I'm going to talk about the system requirements. Obviously, this is like a wish list that we're just going to keep an eye out for whichever system we decide on. So the first one is mining efficiency. A note on this, I think it should be important to maximize the volume our excavation system can hold this year. I know in past, we might think mining speed matters, but especially if we're planning on a 2-robot idea, we would want the excavation to mine a larger volume. Ease of manufacturing and assembly. I think our robot did well in being pretty modular and that we can take excavation off of the drivetrain. And that's also really good when traveling with the robot. So I think it's important to make sure that we can, do maintenance on certain parts and we're not welding things together or riveting things that we'd want to take off in the future. Reliability and life cycle. The robot, especially if we want to increase how much we test it, it's important to make sure that we have very sturdy parts that are able to be replaced as well. Weight saving, this is definitely going to be a big conversation depending on what system we choose. To fit within the maximum dimensions, the speed in completing full excavation deposition cycles within 30 minutes or 15 minutes for our UCF runs. Once again, these numbers can very much change depending on what system we choose. And then to successfully integrate with the subsystems, including a compatible design with the 2-robot. One point that isn't on here is dust mitigation. I think we took a better step towards dust mitigation last year with our cover on bucket elevator, but I would like to see more dust mitigation in excavation and how much regolith we kick up.
Hello, my name is Yasha Scantella. So the first design we had was for the bucket elevator, and the few things that to say about the bucket elevator are that it's easily automatable, it's durable, it has multiple redundancies, and the mining speed is slightly above average. Another good thing is we've done this a lot, so we know how to build bucket elevators. And finally, it's compatible with the 2-robot strategy and favorable for the new format, which emphasizes automation. It can be somewhat likely to jam and has a higher expected mass than certain other stuff. But those are the main benefits of the bucket elevator.
Hi, my name is Sam Cow. Our second idea is SCUP. For those that don't know, it's a rotary mining system where it spins one way, it'll excavate while depositing in the main drum, and when it spins the other way, it'll deposit just regularly. Onto the pros and cons.
Hi, my name is Aiden Crisco. Looking at the pros for this one, the autonomy for it is easy due to having a low amount of moving parts, which allows us to run very simple systems. As well, it's really good for a two-bot system as it's able to consistently mine and have a large capacity, allowing for multiple rotations. As well, it also gives more data for later years and gives us some designs that we can base future designs on going forwards.
Hello, my name is Obiemi Jamel, and the cons of the SCUP system is mainly comes into the form of its difficulty to manufacture. As we've never done a SCUP system, we would have no experience. We would have no experience with the process in manufacturing, so we'd have to come up with new and innovative ways to manufacture the drum, especially with its circular sections. One side being a half circle and the other side being a half circle as well. Additionally, the drive team would have to team would have to accommodate drastic differences so that they could accommodate the drum, as this would be significantly different compared to the bucket elevators that we've been using over the past couple of years. So they would have to create a new design so that they could accommodate these drums. Additionally, it would be a lot more heavy compared to other designs, as the drums would be significantly more metal utilized in the manufacturing. So they would be a lot more heavy, which would also add on to the total weight of the excavation system. And additionally, we've just never built a SCUP system. So our design methods, how we would implement it into the other aspects of our rover would have to be completely designed from the ground up. And simply that makes it a little more daunting to utilize.
My name is Connor Scargill. So when we were thinking about how to innovate on the SCUP and do some more new stuff, to be honest, the general design of the SCUP, it's pretty simple. There's not much to innovate. However, what we did look at is how we could better integrate it with a two-bot system. Because like we said before, with the large holding capacity and the ability to constantly excavate, it's really good. However, the two main issues we found were that with the typical SCUP design that has excelled in competition, the one with one large drum, when the drum deposits the regolith, it goes along the whole width of the mouth of the drum, which makes it much more difficult to accurately deposit. And the other thing is that when you deposit, you have to stop mining. So our solutions to that is, the solutions that we found for that was that we would, instead of one large drum, do two smaller drums. That way the deposition area, when you deposit and you spin the drum the opposite way, it goes along a shorter mouth. That way it's more accurate. And then what we would also do for just a little bit of extra efficiency is if we have them on separate arms, we could keep one drum constantly excavating while the other deposits. That way you don't have to, or we don't have to completely stop the excavation process.
Hello everyone, my name is Ashita. My group was in charge of coming up with the design for a bulldozer. In past years, our bulldozer idea has kind of been like a U-channel pushing dirt into the excavation zone. But as Alex explained, the layout of the competition field is not conducive to that this year. We kind of have to travel a little bit more between excavation and deposition. So our idea has transitioned from a bulldozer to more of an excavation scoop. We've noticed also in past years that just bulldozers aren't always the most efficient design because while they are able to scoop up the dirt, they don't always deposit it all the way. So our design has considered that weakness from past years, and Hayden will explain more about the excavation scoop design.
The way that our design works is it uses two high-powered linear actuators to raise and tilt the bucket. The first linear actuator is attached from the base of the robot to the arm of the excavator. That will raise and lower the bucket, giving us the proper ground clearance to operate. The second linear actuator is going from the arm to the bucket, allowing the bucket to tilt to both scoop and deposit regolith. The reason that we chose this above a standard bulldozer design is because a bulldozer has to push horizontally into the regolith, which with the poor traction of regolith means that most robots cannot get a significant amount of material in their scooper. We are deciding to scoop vertically into the ground using the weight of our robot to get a tremendous amount of regolith and then safely carry that to the deposition zone without loss of material. And now Ella will further elaborate on the benefits of our design.
Hi, my name is Ella Marks, and originally when we were looking at the bulldozer design, it seemed very promising. One of its main advantages is its simplicity. As Hayden mentioned, there are only two linear actuators, which means two motorized points. And that means that there were very few opportunities for system failure because it would be localized probably in those 2 points. Another big advantage was the high volume capacity, just from the sheer size of the bucket. And the speed in which we could excavate was fairly advantageous as well. It would also be fairly easy to construct this because, again, the simplicity of the design, and it wouldn't require much material. It's also very modular and able to move around, at least in previous years, move around the course fairly easily. Ultimately, though, we decided that our advantages were not enough and there were more negatives than positives, which a DT will get into.
Hello, my name is Aditi, and I'll talk about the 3 major disadvantages that we found with this design. The first one is that when the lever arm digs into the regolith, it creates very large cavities. If we got stuck in these cavities, it would be very difficult to get out of them, and we would waste precious time and energy doing so. Secondly, our club has never attempted a design like this, so compared to something like a bucket elevator, it would be very difficult for us to both envision and optimize and test within one competition year. Finally, it's a very incompatible design with the 2-robot system, since there's a hard cap on the amount of material you can excavate in one cycle. And since the cycles are very quick, the lever would be holding regolith for most of the time that the small robot is traveling. And these 3 disadvantages combined outweighed the advantages, as Sienna will talk about.
Hi, my name is Sienna. Though this design had many advantages, it did not score as well when compared to the other designs in the test study. This is because there are so many unknowns, especially since our team has not used it at competition before. It scored very well in having a low mass and having a very high mining speed, but it lacked in being autonomous and being compatible with 2 robots.
Hello, my name is Peter. Our 4th design is the dumpster made by University of Illinois Chicago in the last year's competition. Hi, my name is Anurag, and the way this system would work is by taking a bucket and essentially shoving it into the ground and driving forward to get as much regolith as possible into that bucket, and then driving to the deposition zone, where it would then vibrate to shake out the regolith and increase the volume by simply fluffing it up.
Hi, I'm Austin. The advantages of the system are that it would mine very quickly because it can hold so much volume. We saw this in last year in terms of how much volume it was able to move. And because of the design, it also removes a lot of heavy components, so the mass will decrease.
Unfortunately, this design has many disadvantages as well. We decided to outweigh many of these advantages. Firstly, we believe it has very low compatibility with 2-robot system because it has to stop mining and transfer the regolith into the second robot. We also have no experience with the design, never attempted something like this, and we have very little examples to look at from the past. We also believe it would struggle to be fully autonomous because of the complexity in its complete one cycle of mining operation. And there's a high risk of getting stuck because it digs pretty deep holes.
Hello, my name is Sid, and me, Connor, and Toyin, we did the design research for the auger. Our design for the auger is pretty simple. The auger is just one pretty much big screw that's attached to a specific angle, to specific points on the frame of the robot, where it goes in, spins, it takes the regolith, deposits where it needs to, right? And we were in charge of figuring out what the advantages and disadvantages of it would be, and I'll have Connor come up and talk about the advantages of the design.
I'm Connor, and some of the main advantages we found with the auger is that you're able to continuously excavate. This means that the auger can always be mining, always moving regolith into deposition. It can also mine deep in a small amount of area, so you won't have to move as much. It's very easy for us to get an auger system because rather than making it ourselves, there's lots of stores that we're able to purchase it from. And it's very easy to move the regolith into a deposition system from the auger. Then Tongyu can talk about the disadvantages.
Hello, I'm Tongyu, and I'm here to present some obvious disadvantage of the auger design. First, the auger can be very expensive. By purchasing a whole set of very simple electrical ice drilling auger, it's almost cost about $200. And for professional auger for conventional earth soil digging, please attention, earth soil digging, it costs about $500. It's only cost for purchasing the sets of auger, not considering the cost of making it compatible to moon regolith and also making it compatible to our overall assembly. And second disadvantage is it's difficult to optimize. And the third one is we have almost no pre-existing knowledge to design the auger digging system. And the fourth problem is the auger design can have very slow mining speed. And fifth, the auger can be very heavy. And sixth, since the auger is always spinning, its rotational momentum might cause the loss of a regolith while it's spinning, and obviously NASA probably won't like our regolith dust to spin around, and it might cause some damage to our scores.
And then in terms of using it as part of the 2-robot system, we feel like it'd be better utilized as a way to get the regolith out of the main robot into the other robot. That being said, there are probably more efficient, less weight, less heavy, and more fast ways to get that done. But we just felt like that needed to be noted.
All right, so after we get done each of the designs, we conducted a trade study in which we used criteria of 2-robot capability, mass, mining speed, experience, risk, and autonomy capabilities, and weighted each of those criteria against each other, weighted each of the designs against each other for each criteria, and the results are on the screen, with bucket elevator being the clear favorites and the design we'll be going with in the future. I'll now open the floor to questions. Yes.
Why is Scump's mining speed rated so lowly given the performance of UVA at competition last year?
Yeah, so SCUP has a low rated mining speed, more in comparison to a bulldozer and dumpster who still mine significantly more at competition. I believe that SCUP, when optimized, has similar mining speed as a bucket elevator optimized. However, I do believe in a field situation as last year, those two designs would still fall short in pure volume in compared to a bulldozer and dumpster, and that's where I weighted the mining speed. Yes.
I do agree that certainly SCUP is worse than a bulldozer and dumpster, but bucket elevator could outperform SCUP by a significant amount, despite two pretty good bucket elevator teams, Alabama and Michigan Tech, mining significantly less material than UVA's SCUP last year. So I'm wondering where the justification of bucket elevator's somewhat high mining speed is, comparable to dumpster, who mined almost 100,000 cubic centimeters more than both of those bucket elevators in the first round of KSC, despite being outperformed by SCUP.
Yeah, so bulldozer and dumpster are both weighted the highest, with bulldozer, you can see 2.1 or 0.21, dumpster 0.18. And then bucket elevator and SCUP are 0.13, 0.07 respectively, right? And I may need to look and reevaluate the way the trade study was conducted, because I believe that bucket elevator and SCUP may have equivocal mining speed. Have both optimized, but I also believe that the bucket elevator designs we saw competition last year fell short of what we believe is the fully optimized design of what we'll be going for this year. So this may be an optimistic evaluation of the bucket elevator, but we may need to reevaluate the trade study based upon that. Alex?
Can you go back to your combination slide that has your mass estimates?
Yes.
So I noticed you said excavation would be 10% each kilograms. I believe the numbers put on the actual slides earlier was around 1 meter. Which one is accurate, or am I just misunderstanding?
I believe that the 20 estimates is an overestimate, but anywhere 20 was the estimate we can go for.
Okay.
I think it's all also these numbers don't mean anything towards the side of system, so.
Fair enough.
But yes, for our excavation system last year was around 18 kilograms, and we believe there's a lot of weight-saving ways, such as using carbon fiber structure rods that could benefit and lower the mass. However, just some of the ideas we have for optimizing the bucket elevator design will increase the mass overall. So we expect it to be about similar, around the 18 kilogram mark this year.
Okay. Cool. Thank you.
John?
Do you guys have a target excavation rate? Because I know last year it was around 0.2 meters per second. Do you think that influences the volume of the 1.2 system or not?
Yeah, that's a good question. I don't have a numeric value for the excavation rate we want. I find that challenging to find a actual value, especially when we don't know the capacity of deposition quite yet. However, we expect it to be about 1.5 times as much as last year. That was the goal. Yeah.
The slide that had all of the values of how much or how important something was. Are there any other variables in the kind of design process that I need to worry about that aren't listed here, like deposition speed or anything like that?
Yeah, that's a good question. Whether or not there's other criteria we should be accounting for. There definitely are, such as dust mitigation and other things like that. However, these are the 5 criteria that we consider to be most important when considering which design to go for in the future. But there are more factors to consider when we're actually designing the bucket elevator. In the top.
Would you remind me what you mean by true robot compatibility?
Yeah. So this year with excavation, obviously the 2 robots change does not affect excavation too much, as we don't have to design anything for the second robot. However, we still want to make sure that our design is fully capable and compatible with the 2 robot system. And so the reason why you may see bucket elevator have a higher and the highest 2 robot capability score is because it has the ability to continuously excavate during the entire run and store all of its material within the deposition system, whenever a system such as Bulldozer would just be able to accumulate their excavation cycle, and then they would have to sit and wait for the deposition robot to come back to the excavation zone. So we believe that designs such as the bucket elevator and the SCUP, which both have the ability to continuously excavate for the entire portion while the deposition robot is traversing, is the most beneficial. Peter?
So for the SCUP's two robot compatibility, would the idea basically be that we sort of just mine and fill up the SCUPs and then turn and deposit those in the, and then just turn and dump those into the small robot that comes back?
Yeah, so the idea with the SCUP capability is that we would just be mining the entire portion, and hopefully we don't run into any volume issues with the SCUP during our excavation portion. And then we deposit into the small robot, the deposition robot, to deposit in the deposition zone. The reason why it is scored lower is because accurately depositing with a SCUP system is difficult, and the deposition is also a slow process in comparison to a set aside deposition system.
I also think the SCUP, like the way UVA did it, was probably the correct way in terms of making a really large SCUP and then building a robot to balance out that way, like a very tall system on top to balance it out. And I think pairing, if you want to do a SCUP for a mini robot, I would almost do the iPad SCUP that would actually out and then mine on the floor, but it just makes no sense to dump it into a tiny robot.
Yeah.
With the SCUP, in terms of the two robot compatibility, would it not make more sense perhaps to basically at that point make two identical robots that both have SCUP? That way one can be mining while the other's heading to the deposition deposit, and then just rotate between the two zones.
Yeah, I think honestly with something like the SCUP, Bulldozer, or Dumpster, if we were to go with either of those three designs, we would have to completely scrap the two robot idea entirely. I don't think those designs are very compatible with two robot at all. And I think that their benefit is in quick cycle times, or with SCUP, just having as many SCUPs or the most volume in their internal storage as possible.
I feel like that almost goes back to Pat's point too, just two identical robots. I understand what you mean by just two SCUP bots that are rotating zones. I think that would make more sense than just one big SCUP in a little deposition pod.
Any other questions? All right, I will be turning it over to deposition.
I'll just wait until excavation gets settled. All right, for deposition, a quick overview of what we'll be presenting today. First, we'll go over our goals, system goals, then into our 5 designs, then lastly with our trade studies and final decisions. So in terms of system goals, overall, we're looking at improving our integration from last year, resolving issues with mounting that we had last year. We're looking at deposition speed and volume, increasing that. Of course, manufacturability, reliability, and risk, and dust mitigation, improving upon our trianglegrams from last year as well. In terms of the 2 robots idea proposal, a large focus with that is the integration between the 2 robots, meaning focusing things on making sure our deposition system on the main robot is high enough to drop into the mini robot. And then for the mini robot itself, it's looking at how fast it can run and also containing as much as the main robot. In terms of our specific aims, we're looking at improving upon last year, that being a faster deposition speed of 5 to 7 seconds, increasing our volume to possibly more than 20 liters, and then that might come with the cost of a higher weight, so we put it around 10 to 13 kilograms. I'll hand it off to our designs.
So our first design idea is the conveyor belt. It's the design we ran with last year. So regolith would be stored on top of the belt, and then when the belt is activated, it would disperse the regolith out the back. If we were to choose this design again, some potential improvements could include a back flap to improve the storage and potentially integrating the motor within the belt to improve integration. Some pros with this design include the experience. We've made this belt before, so we could focus more of our time focusing on the improvements that I mentioned previously. It's proven to be reliable. We've taken it to competition and it's performed relatively well. It's easy to integrate with the other systems. Again, we've had experience with this before, so having the other systems integrate around it would be pretty simple. And then compared to other methods, it's pretty quick when it comes to deposition of the regolith. When it comes to the cons, there's a lot of moving parts, so being able to protect all of them from the dust created by the regolith would be a challenge. Additionally, if the regolith were to damage the belt in any way, it could affect the speed of the deposition and the reliability. And then finally, if we were to choose the conveyor belt for the small robot, it would have a much harder time integrating the other systems around it as opposed to something like a dump truck.
Hi, I'm Tommy. I'm going to talk about the dump truck design. So essentially what this design boils down to is it's just stored in a large bin that'll tip over. There's also a door at the back that'll allow regolith to just sit there until we dump it out eventually. I'm gonna skip over the potential improvements for now, we'll get there. So the pros for this at least is it's mechanically simple. It's just one motion where a linear actuator will allow it to rotate upwards and dump it out the back. It's also pretty fast and consistent as it's just another one motion. And it's also a controlled exit point. It's not shown in this diagram, but what we proposed was a funnel in the back where it's more controlled, and that's assuming that there's also a 2-robot system. It also works in 1 robot. It's also large and expandable. So you can either, this shape has it a more like triangular prism. You could also have it a rectangular prism or just taller. It's very easy to change it. The issues with it though are it'll stick to the bin. As you can see in that diagram at least, it'll definitely stick to the bottom. It also requires stronger hardware, so like a motor, more powerful one for this rotation, because all of it will be most likely stored further away from the rotation point. It's also difficult to integrate with a bucket system, especially just because of how much space it's required to tilt up. And obviously potential tipping. This is more likely on a mini robot where it's the only thing on. And so when it's tipping over, all of the center of mass will move to one side and it could lean over and tip. So addressing the regolith issue, adding a vibration motor just to the bottom of the basin will allow at least some of those smaller particles to unstick and come out smoothly. This also does pose another issue of just dust, but overall dust mitigation is pretty good with this design, as most, if not all of the regolith will be contained inside of that bin. And there's really no other way to get it stuck in any of the motion systems. For the mini robot, it's not on the slide, but mini robot, we proposed this because it's really good for the mini robot, just because it's super low form factor, at least height-wise. I'm gonna move on to the trapdoor system.
Hi, I'm Akshay. I'm on the trapdoor design. So this isn't a regular trapdoor. I couldn't really find a real world example, but I called it a retracting trapdoor. So instead of extending outside the robot's frame, it opens into the side of the robot, of the container for the regolith. And the pros are that it's probably from the designs that we've come up with, it's the fastest method of deposition and it's easy to manufacture and it's pretty low weight. And because it doesn't extend outside the robot, we can have the second robot drive under the trapdoor so that we can deposit down onto the second robot. And the cons are that it has a large profile and the small robot needs to fit under the main robot, which means we need a high drivetrain clearance. And it's potentially difficult to dust proof because there's quite a few moving parts and a lot of gaps in between. but we've been looking at different types of flaps that we can cover these gaps with, as well as brushes. And
Hi, I'm Brandon. I'll be focusing on the auger method today. The auger is a rotating helical screw that conveys granular regolith on a tube, of course. Excavation talked about the auger before. They don't have experience with it, but one of our pros is that we actually do have experience with the auger design. It has a very controlled deposition rate, so you're able to control how much and how fast you can deposit regolith into the behind. It has very high deposition accuracy, which is very good with a 2-robot system, as you're able to take it from the big robot to the small robot very efficiently, very cleanly. Some cons, it's very prone to jams. If it jams, it's one of the biggest failures of the system. There's some difficulty in sealing with the jams, of course, and it has very high friction wear. So over time, it'll be a very high maintenance part. It's harder to manufacture. Excavation talked about buying it, but it would be very heavy, and it has pretty low deposition rate and a pretty low deposition volume. So you can't hold as much within the system itself.
Hi, I'm Aya, and I'll be covering the piston design. So how this system works is basically there's a small linear actuating piston that extends a wall that pushes up the stored regolith up to kind of the edge of the container that basically just pushes it and makes it fall out into the deposition zone. This makes it pretty easy to seal for protection from regolith dust. And since all the parts are basically, all the operations are in the sort of same housing area, the integration is pretty simple and doesn't interact with the other systems very much, but it does have a lot of cons. The geometry makes it so that the storage space is pretty limited, so it's not very viable for a mini bot, as you know, not much volume, and it is pretty slow because the speed of the piston is also pretty limited, and it's pretty difficult to manufacture because the tolerances needed for all the parts are very specific, and this reduces the reliability of the system quite a lot.
My name is Peter. So after coming up with all these designs, we've conducted a number of trade studies evaluating these designs, both on the basis of just having a single robot and how they might interact with the two robot solution. This trade study right here represents our analysis of them for a single robot. We were looking at 5 factors in this trade study: deposition speed, integration with other subsystems, the deposition volume, the possible manufacturability, and the reliability of the system. For one robot, it's a pretty close call between conveyor belt, trapdoor, and dump truck, but we do think conveyor belt would be the best solution. The conveyor has a number of benefits. It's quite easy to integrate with the other subsystems, especially if we integrate the motor to be contained within the belt itself. But it's a little bit more difficult to manufacture, mostly due to some concerns we ran into last year and actually stitching the belt together. The trapdoor is faster in terms of the deposition speed, as it's all a one single motion regardless of the amount of regolith, and probably a pretty quick motion. However, it's also harder to integrate in terms of making sure there's nothing else beneath it, and also all the dust concerns that were previously mentioned by Akshay.
For the two robots, the kind of thing that came out the most in terms of our criteria, which is comparable to the last trade study, is really the integration between both the two systems and on their robots individually. For the main robot, conveyor belt stood out the most because of this being just better in terms of integration, where the dump truck might hit the excavation system, and trapdoor auger piston just don't perform as well in terms of integration. And then for the mini robot, it was more of a jack of all trades. The dump truck came out on top. And that's what we got. Any questions? Alex?
On your main slide, you mentioned you were having an estimated volume of 20 liters.
Yes.
That is the same as the SDR value from last year. Are you considering making the system the same size, or are you considering expanding it?
Last year, our like the actual liter in terms of liters wasn't actually ended up being 20 liters, right? So that's still a higher estimate. I do hope that we make more than 20 liters though.
I would also say that I think based on last year's design, it's very possible that with an equivalently sized system, we could hold more regolith. There was a lot of losses in that system due to not having a flap on the back, meaning that we couldn't pile up regolith against there, and having to have basically also not a flap on the front due to having to make cutouts for clearance with the excavation system. So by improving both of those, we could, and by basically putting walls on either side of the conveyor belt, I do think we could drastically increase the amount of regolith held in the same volume.
So to clarify, 20 liters is more of a lower bound than a upper. So you're estimating you're going to hold maybe 30 liters on it if everything works out right, but you're saying 20 just kind of stations.
I think it's possible. I think 20 might be more of the goal than sort of the minimum. John.
So it's looking at the model for a single bot and two bot, the difference between a 20-liter system and like a 50-liter system, which is what drivetrain could carry with a 130 kilogram weight limit, is 350 points and about 600. So like trying to increase the volume for single bot is like super important, it seems like. And then two bot system though, kind of handicapped by excavation rate. And with our previous year's excavation rate, that volume, that ideal volume would be like about 30 meters.
All right.
The 130 includes all of the subsystems that get put on top of the drive.
Yeah, that's
which is about 80.
Yeah.
Yes. And then the other 80 is about 20 meters from a little more.
So 50 kilogram bot, 130 kilogram total. 80 kilograms in both systems.
It does include all the subsystems that go on top.
This sounds like more of an internal drivetrain discussion, but I think the design, the insight into potential point scoring is valuable.
I have two questions. So you pose like tipping concerns for the dump truck, and given that you put the dump truck on the smaller robot, if I understood correctly, like how would you, because with regolith, like it sticks a lot, would you attach some sort of motor to like vibrate the system, or how would it just be such a steep angle?
Yeah, like with what Tommy had proposed, having that kind of vibration motor like how you have in your phone, to just try to shake it off, I think that could be a pretty effective way to do it. And then you were talking about tipping a little bit too. I think there are ways for us to mitigate that, maybe adding like a supporting rod when the door opens up to prevent any sort of tipping if that does occur. And then.
Yeah, I think also it's, if we're going down the dump truck route, we might be able to look into materials that would perhaps stick less, or trying to get a very smooth finish. But I think that the motor and such is ways to try to mitigate the amount of dust that's sticking.
Can I see your trick studies again? And then I also have a question.
For one robot or two robots?
I could just look at both of these. Two robot. So you guys didn't consider like mass. Do you think like conveyor belt would be lighter than a dump truck on a smaller robot?
It's hard to say right now. I think they'd probably be fairly comparable, or conveyor belt would be heavier. Okay. I think it would depend on what kind of materials we can find for the construction of the dump truck bed itself.
And have you guys played with the idea of like the mini robot actually being our excavation robot, and then we just have an extremely large deposition robot, almost like a very low to the ground conveyor belt? Like, would it would probably make more sense?
Maybe more overall.
I mean, the two robot, all of that in general has a number of is a very inter-team discussion. I think about that. The question continues to become, well, then where does all the regolith go, right? Is the excavation robot just idling there while the deposition robot goes and dumps? And in that case, what's even the point of having two robots when you could just have one robot, one really big robot, right? So I would say my analysis still states that the deposition systems on both would have to be relatively equal.
Do you think
intuitively conveyor belt would be lighter than the dump truck on a small robot?
Intuitively, I would say I honestly, intuitively, I feel like they might be, it's hard for me to say. I think, I could see it going either way.
Yeah.
Alex? Yeah?
So on your dump truck slide, one of the cons you mentioned was that you needed a big and powerful motor. So have you considered using something like a linear actuator instead, so you wouldn't have to deal with the pivot points?
Certainly.
Cool.
Let's go with Ankur, I think.
Have you considered using the conveyor belt? Have you considered angling the conveyor belt upwards, but at the end of it, that you could increase the volume, having the starting point close to excavations and pull further down into the drivetrain system?
So you're saying excavation is like this, and then the conveyor belt is like this? Yes, certainly that's a consideration, and something that we would definitely be interested in doing, and which would probably be improved again by sort of enabling that ability by moving the deposition motor into the belt. Yes, you.
When you guys were considering the dump truck, or the dumpster, I guess, idea, did you consider like the dump trucks that have a removable bucket? Kind of like how when moving out of the house, they'll leave the bucket of the dump truck in the driveway, and you can just continue to load it up until the dump truck's ready to pick it back up. Kind of similar to how we're continuously loading up the dump truck as the dump truck's awaiting other things, and then we just have multiple buckets so we continuously fill and continue to take over and over again.
I mean that's definitely very interesting. And potentially a route to take in terms of integrating for sure. It'd be interesting to see sort of the cycle time, because it sounds to me like in creating that into a full 2-robot system, there would have to be some sort of exchange time in terms of the small robot coming back with its dumpster and then parking that and then grabbing the big one and then putting that down and then grabbing the small one and loading that into excavation. But that's certainly a route that we could look down, and that might be very interesting. Will?
Looking at excavation and deposition integration, since you all are going with a conveyor belt similar to last year, I know you mentioned the front flap, which we had to excise.
Mm-hmm.
Do you see any other additional ways we can improve the integration? I know Ethan and I will be discussing this a lot during the design portion. But
If you're going with a bucket elevator, making it at a steeper angle, more slanted angle to the ground would be a less vertical angle, would improve that significantly, because then there's more overhang, right? And so then we can, because the problem was that it was very, very steep, which meant that or very, very, vertical, right? Which meant that the buckets had to sort of come back down this way. But if we have it instead sort of like this, now there's much more sort of vertical space here between here and the buckets, is what comes to mind immediately. Kyle, you had a question, right?
Kind of now branching off of the changed bucket idea, or changed deposition system idea, you mentioned that you need to have your deposition systems the same size. Yeah, and then you mentioned the transfer time potentially being the points of loss. If you did a exchangeable storage system, would you not be able to then just have a small deposition system on your main robot that then just holds any material line during the transfer?
Sorry, I don't quite understand what you're saying.
So if I was understanding the removable bucket design,
Mhm.
where you would have, I would assume, 2 large buckets
Yeah.
that you would put regular into.
Mm-hmm.
But with you had mentioned that you would have to stop mining during the time that you are swapping out the whole bucket.
Oh, I think I get what you're saying.
So just keep it so that you have a small deposition system on your main robot that holds material during that transfer time,
Mhm.
that then gets rejected. Do you think that potentially could remove some of the problems?
Yeah.
It would also make your main robot much lighter.
And this is in discussion to the sort of swappable dump truck bucket idea. certainly, I think that could be a way to sort of mitigate any losses. There would still be some amount of an increase in the cycle time for deposition because there still has to be that exchange, and that certainly the exchange itself would increase complexity on software's time, but they've got people, and I believe in them. But yeah, that's certainly an option and a possibility to improve that idea.
Alex?
A little bit ago, you mentioned with the deposition and excavation sizing, that if there's a two robot system, deposition needs to be big enough that excavation does somewhere to mine, you're going to just mine all your stuff and the main robot has to sit around waiting for the main robot to come back. Are you concerned that will happen with your current system volume, or do you, especially with the increased excavation speed, or do you think that the current volume counts?
If the volume stays unchanged from last year, then definitely. I believe we would a standard trenching run would essentially fill up last year's deposition system to a pretty high amount of the capacity, and that was about 30 seconds, I believe. So my understanding is that would be a concern. And so that's why, there are ways that we can increase the storage capacity of the current deposition system. And there's an extent to which certainly the system needs to expand in some ways, which there are things that we can do to facilitate that.
Yeah, I think it would need to be, what is the minimum volume we need? I think would be a longer discussion later. But
Certainly.
Cool.
Will?
I know that for excavation, looking onto the bucket elevator design, where you are heavily considering wider buckets, do you all see there being a possibility of making the deposition system wider?
Yes.
Yes.
The main thing that facilitates that, again, is moving the motor interiorly to the belt. And once we do that, then we no longer have to contend with getting the power sort of through the center of drivetrain. So then we can expand it out to the sides. That might be concerning in terms of electrical box placement, but that's another concern.
Last year, you mentioned that the manufacturing for the conveyor belt was hard. Would you guys look into a continuous rubber piece, or was it the spline that you had? Okay.
The belt last year ended up working out quite well, but certainly a continuous piece would be better in terms of sort of consistency and usability, and I do think we'd be better at making a belt this year, and I forget if we have any material left over. I have no idea, but certainly looking into a continuous belt, it was challenging, I believe, to find suitable belts, but potentially with new,
a larger system.
Yeah, potentially with a larger system, that might be easier for us to find.
Any other questions? I'll hand it over to drivetrain then.
Yep.
Cool. So for drivetrain, this system overview is for one bot. Two bot will be talked about at the end of all these slides. The system goals, the gearboxes will remain the same. Chain versus shaft, we'll talk about that. We've also looked into skid plates after last year's second Kennedy run. Also wheel design, some changes will be made. What onboarding members have looked at is dust tolerance mechanisms, so they will be presenting their ideas as well as their trade studies for those, and then mini-bot will be discussed. The system goals, the weight of drivetrain for one robot is about 20 kilograms is the upper limit of that. Last year we had 19.6, so 20 kilograms is a good upper limit. These are the size dimensions as well for that. And then we believe it can support 130 kilograms. That is also an estimate. It mainly depends on what subsystems are selected.
which includes how much each subsystems weigh. Also, we want to be able to traverse at a 30-degree slope, which is a good estimate for most of the rocks as well as pits that Kennedy and other Florida has. And then we also want to focus on making our system reliable, be able to carry lots of weight, light, and then easy to manufacture.
As for our gearboxes, our current plan is to stick with our two 200-watt motors with our 50-to-1 attached gearboxes. And then for traversing around 18% motor power to give us about half a foot a second. With these motors, it's 32 newton meters of rated torque, 92 newton meters of peak torque from what we've seen. And then for the rated speeds, about 60 RPM with 80 RPM peak. Our plan is to stick to one-to-one gearbox gearing to separate our motors and wheel shafts just for ease of space. And then as for the gearbox itself, we plan to stick with a box tube design with the major point being 3D printing most of the pieces to design test for assembly, which was a major problem we ran into in previous years.
All right, hi, I'm Sophia. I'm going to talk a little about sticking with a chain drive system or shifting to a shaft drive system. So from our analysis, we decided to we were going to stick with the chain drive system. Main reason being, we know how to do it and we know what went wrong last year, so we know what to do to fix it. It has good power conversion and it's easily accessible and easy to maintain. The main thing here is going to be designing a proper chain tensioner and putting more thought into that than was put in last year. And I'm going to turn it over to John to talk a little about why we didn't go with the shaft.
So the main reasons why we didn't go with shaft was mainly because of we're more experienced with chain and we know the issues went wrong last year. And then some considerations we went with shaft would be getting 90-degree gearboxes instead of making our own. It would allow us for easier manufacturing. However, it would add additional weight and cost to the robot. And then we also looked at different types of gears that we'd use for shafts, such as like a worm gear, and then also differential gears. And the main issues with that is worm gears aren't really efficient, and then differential gears are easy to shear, which would be a main problem if we had to repair it during competition.
My name is Darren, and I did the skid plate trade studies. So basically, the entire point of the skid plate was to get us unstuck. Like last year, we got stuck on the rock, we couldn't get off. So the whole point of the skid plate is to help us get off and continue our run. And so I came up with around 4 ideas. There's only 3 on this trade study. There's like a parabola bottom skid plate, there's like a pot belly, and then there's like a wavy bottom skid plate, which is like a sine or cosine curve. And just some general notes about all 3 of these, they're very hard to manufacture. The easiest way we're gonna do it is 3D printing. There is metal bending that would be very difficult for like the pot belly and probably the wavy bottom because we have to get the dimensions right. And then a new idea that came up recently was metal casting. We would probably do that through an external source. So we would send our design to them and they would send it back. And then there's also hydroforming that came up recently where we would use a pressure washer from the BIDC to form these shapes. And here's some designs. So on the top left here, we have one of the parabolas, and then on the top right, we have another parabola, but just oriented differently. So if we look at the top left, it would be curved from the front frame to the back frame, where the top right would be from the side frames to side frames, and it would help us tilt off like the certain obstacle that we might get stuck on, so we can get a little bit of traction on the wheels to pull us out of it. On the bottom left, we have the pot belly. If you think of like a metal bolt, it would be attached to the bottom where it would help roll. I mean, all of these help roll the robot onto its side, but it would be better in any way that we hit like an obstacle, it would roll off to the side. If we hit it from the side, it can roll off to the front. And then on the bottom right, we have the like wavy cosine sine shaped
chain guards. So basically, it would help if we if we hit it straight on, and we got stuck a little bit. The back would be tilted. The front will be tilted up, and then the back, the wheels would still be there, so we could just back up off of that, helping us not get stuck on those rocks. And
I'm Anthony. Sorry. I'm John. We worked on the wheel redesign. I will be talking about the grousers. Through our trade study, we concluded that perpendicular grousers and angled grousers were the best options. Perpendicular grousers are where the grousers are just perpendicular to the rim, and angled they would have an angle to the rim, allowing for better point turns. And our main criteria were traction and mobility. Traction is the ability for the robot to push itself forward, and mobility is mainly its turning. We concluded that box grousers, which was our last year's, has the best traction. However, it had not so good mobility. As it turned, it would just dig itself into a hole. And for our ideas, we currently have 5. We have a box grouser, which is our last year's idea. We have 2 years ago rigid perpendicular, so the rim would be made of a rigid material and allowing for better point turns than to the box grouser. And then we have our spring steel mesh, which would create a compliant wheel with angled grousers. And we also have the rigid diagonal grouser design, and John will speak more about the compliant.
Okay, so I'm going to speak a bit more about the criteria here. Notice the lack of manufacturability and cost. This trade study only had 5 criteria, and we figured that these other 5 kind of are more important, and the other 2, cost and manufacturability, should be constraints. Can we actually pay for these wheels, and do we have the resources at Purdue to manufacture them? So I'm going to talk a little bit more about these criteria because I think they're super important. First, we have weight and efficiency. That just straight up gets us more points, right? We have a lower weight wheel if we have more efficient wheels. And then we have traction and mobility. Traction, you can think of it as like how steep of a slope can the bot traverse. And then mobility is that thing that the box grouser group sucked last year and the wheels before, and kind of is what started this whole wheel redesign. And that's like how well can your bot turn with a skid steer based drive system. And then finally, we have terrain versatility. This is especially important because we lack a suspension system. So being able to go over various terrains like big giant holes in the ground and rocks is super important. So we don't get stuck like last week. Okay, so these were the results. Number 1, we have spring steel mesh. Of course, this is probably super high because we don't have manufacturability as a criteria. And so as of right now, we think we have the resources at Purdue to manufacture these. I really, really beg you guys to dig in on this and ask us a bunch of questions about it, because we want to figure out, before we spend more time looking into this, whether we actually do have the resources at Purdue to make these. And second, we have rigid diagonal grousers. Those were the Utah's wheels. In the top right there, you see Utah with the red wheels. And next, we have compliant diagonal grousers. So the manufacturability of compliant diagonal and spring steel mesh would actually probably be the same. Similar, because you're probably going to have some kind of spring steel leaflets or like composite part in order to get that compliance. You can think of the spring steel mesh as just, instead of those little, you see the blue arrow, the spring leaflets, you can think about those rotating like 90 degrees and then wrapping around the whole side. Both would probably include like having some kind of furnace to, temper and harden the spring steel. So those manufacturability wise would probably be pretty similar. I think that's about it. There's some interesting trends that you can see that generally you sacrifice traction for mobility. The difference between the compliant diagonal grouser and the spring steel is basically we believe that the compliant diagonal grouser would have a bit higher efficiency because it can
basically has a more clean pressure gradient on the regolith versus spring-stir mesh. But spring-stir mesh, we think, would have by and far the best mobility out of any of these wheels, and that would be able to turn on a dime. I think that's about it.
Hi, I'm Alex. My sub-team worked on dust tolerance mechanisms, which is one of the new rule sets that came out. Basically, active dust tolerance, ridding the robot of dust when it does eventually kick up onto the robot. The 4 criteria we determined were weight, energy usage, effectiveness, and implementation. Weight, obviously, how heavy would this mechanism be? Energy usage, how much energy would it pull from the battery? Effectiveness, how well would it actually rid the system of dust? And finally, implementation. How easily could we implement it on the robot? Weight and energy were the most weighted because we thought those were most important. One, weight goes directly into scoring. Energy usage is also very important. Ease of implementation was the next favored criteria because we figured that if it was easy to implement, it was easy to get the points scored because effectiveness didn't really factor that much into the scoring of it.
Hi, my name is Rutvik. So we found that electrostatic removal is actually the highest rated. So basically it uses embedded electrodes on a surface and you pass a low frequency, high voltage current through it, and that creates an electric field. And that basically applies a force onto charged regolith material and basically sweeps it off of the surface. So in theory, this would be really good and might actually be really effective on the moon. But in the context of this competition, there are some issues. So first off, it's actually difficult to implement because it would require a lot of testing and time. And furthermore, the main issue with this is material consistency. So across different fields, in different competitions, the regolith material might not actually be charged. So this solution would basically become redundant and wouldn't even work, which is why we recommend using a different solution.
So I'm Avanish, and so with the issues that electrostatic removal has, our next best option was to use brushes. And so the idea behind this is that the scoring to get active dust tolerance is 5 points if it's on your robot and it's cleaning. So we wanted to have a system that didn't use too much energy and was light, so that way it wouldn't take points away that would otherwise outweigh those 5 points you gained. And so brushes are nice because they're really cheap and simple and easy to implement on the robot. And so what we came up with was just sort of almost like a wiper like this, where you just have a brush on one end and you can just stick that on whichever part of the robot gets a lot of dust and say it's active dust tolerance. So, yeah.
Hi, my name is Sam, and me and my partner Jonathan, we worked and we considered 3 active dust tolerance mechanisms, including the rumble, brushes, and charged plates. Now, we weighed them in our trade study over durability, cost, weight, installation time, and repairability. And we found that the brushes were the clear winner in the trade study, and it's primarily because of how cheap and easy they are to implement. And while making this trade study, we also thought about the weight capacity for the new robot, especially as we've been talking about because of the 2 robot system. We need to be considerate of exactly how much weight we are adding, and adding brushes in the manner we're showing right over here is not going to add a whole lot of weight. And I think that is a very effective way to lose a lot of dust over the shaft. And Jonathan.
Hello, my name is Jonathan. We also saw brushes would be really fast to implement. So we were thinking, what if we added some other source of dust tolerance? So we were thinking maybe adding rumble if we had more time and more capabilities, because that would just allow us to have 2 different systems. So if one falls apart in one situation, or the dust still sneaks through, we would have another system that would be able to remove more dust.
All right, I'm Yash. Our group focused mainly on covering up open areas of our chassis to prevent dust from coming in. So we considered factors like removability for maintenance. Active dust tolerance just is the solution we came up with. Active manufacturability. So most of these are going to be TPU or PLA 3D printed, and then just dust blockage. How much dust does it truly get out of the chassis? So the 5 options we were considering were inner flexible seal, so just on the inside of the tubing, the outer hard seal, so just on the outside of the tubing using a harder plastic, inner and outer flexible seal, which covers both the outside and goes in cork-like into the tubing, which is what came out on top, brush, and the current system, which is a square piece of hard plastic with aluminum tape holding it on. So overall, the inner and outer flexible seal, so essentially using a cork into the aluminum tubing as well as an outer layer of rubber, probably TPU 3D printed, came out on top, despite it being a little bit harder to manufacture as it does require some precision in the 3D printing, and it does not cover the active dust tolerance, so there's a little bit of room for getting extra points there that we're missing out on. However, the other options were not as effective in covering dust, which was our main focus. So I'll pass it on.
We also have some secondary considerations after finding that the inner and outer flexible seal was the best in our trade study. We also have things such as the shape of the inner seal, as you can see in the top left. We have 5 designs that we've come up with, but we haven't done a trade study on them yet, or any other because we're still trying to consider them. Just generally, how do we want to provide, say, secondary ways of catching dust instead of letting it through? What is the weight considerations? Additionally, things like how hollow do we want these seals to be? Because if the seal needs to cover a large surface area, that mass that we need to have adds up quick, and so does the cost, because it's just a big block of TPU, very likely. And so also general dimensions, things like how thick do we want the small outer part to be? How far out do we want it to go? Do we want to allow for possibly aluminum tape going around the outer seal? General specifics that we couldn't really perform a trade study on before we actually make them and put them in place and see which one physically works best in an actual experiment.
Hello, my name is Justin. So while we did include a brush for the chain in the trade study, we are considering adding it in addition to this inner and outer seal. The reason why the seal would prevent most dust from getting in the drivetrain system, but by adding a brush inside, like attached with brush on the chain, it would help if any dust somehow made it through the seal, it would keep it off the chain and prevent wear and tear on the chain. Another reason we would have a brush inside is it would get us the 5 active dust tolerance points for our system.
Hi. Hi, my name is Dill. I feel like we talked about most of the things on this slide, but I did want to mention that the source of inspiration for these stoppers and the design actually came from a lot of household appliances. So you're thinking like, you know how a blender has like that seal that you have open and it keeps all the things blending inside? That was the kind of idea, but for keeping dust on the outside. This would involve a bit of testing to see what sort of design works, what sort of designs are easier to manufacture, and what is the most effective at blocking out dust from the chassis.
Hi, my name is Shrikar, and we also looked at the active dust tolerance system specifically for the wheels. And so we compared 4 different systems: a static ionizer, electrodynamic dust shield, acoustic levitation system, and the brush. And we weighed these against our 4 criteria, which were dust tolerance, effectiveness, cost, power, and weight. And we found a brush to be a clear winner.
We chose to go with the brush because we thought it would be the most effective and efficient design out of all. It would be easy to implement, wouldn't take up too many resources, and we think it would work well too.
Hi, Rithika. I just wanted to explain our diagram. So essentially, we decided that we would place the brush on the back corner of the wheel so that it wouldn't extend out of the length of the robot. And also, we would be able to expel all the dust from the wheels. Also, we would have it rotating on the same axis as the wheel to maximize efficiency. And finally, for the power source, based on the finalized design of the robot, we would either have servo motors as depicted on the diagram, or we would have gears connecting the brush to the motor of the wheel.
Okay. Moving into Minibot, we have a separate systems goal slide for this. The weight of drivetrain for the Minibot is probably only be 5 kilograms. Most of Minibot drivetrain can be 3D printed or it'll end up being very lightweight. The dimensions for it are actually quite large if you consider how big the main robot is as well. That is because length, we have 25 inches left over in length. This is the max of the dimension. And then 8 inches tall. It can be taller than this, but this is what was estimated. And then also should be able to support both the excavation system and the amount of regolith mined. This depends on how wide we make the tracks, which will be a later decision. So this could increase. And then has the same 30-degree slope, being able to get out of those situations because it will have to go through a harder to get through area. Also being able to complete multiple deposition cycles. So looking at the treads, what was mainly looked at is having each tread piece printed and then put together with a pin. Think of like a thin copper wire kind of in between, something similar to that, printing it as one large tread or having tinier versions of the wheels. Those are mainly put in there for comparison. When wheels get that small, they act more as paddle boats, and that's not really effective. So the treads would also be able to carry more weight. Cost-wise, the one tread design will cost more because TPU is more expensive. This would have to get printed out of TPU, whereas the individual treads could get printed out of PLA. The main concern with the individual treads is that regolith could get stuck in between them, causing the system to jam. It also makes dust tolerance for the tread system harder, whereas the one tread design would be easier to work around with that. Printing it, again, is the most expensive part. TPU costs about twice what PLA does. However, the ME 3D printing lab, I've talked to them recently, and if you email them and discuss it with the man who runs the lab, and your print time is less than 8 hours, that is very likely they will let us print our treads there, which could save cost. Yes.
Okay, so if we do have the Minibot and it would go under the robot or something, or it would take up space under the robot, we would need to redesign the skid plate. And so I came up with 2 ideas. They're kind of based off the main one, the wavy gearbox skid plate and the parabolic skid plate, but they would both either act as a chain guard or act like on the chain guard. So it would be connected to the chain guard instead of being implemented in like the center of the robot. And I mean, this depends on whether the Minibot does exist or not and where it does start. So if it doesn't start or it never needs to be under the robot, we can go with the full design from under the robot and we won't have to go through this. But preferably we would go ahead with the parabolic chain guard because it shows the most, it shows better than the wavy gearbox skid plate, and the manufacturability of the parabolic chain guard will be much easier than the wavy gearbox skid plate. Oh, yes. So here's some images. If the Minibot were to go under, as I said, I don't know how to explain this, but on the frame on the outside, there's like a little box under that. That would be the chain guards and the skid plates, and it would still help if we got like beached on a rock or some obstacle. It would still help tilt one side to give traction to the wheels so that we can get out somehow, whether it be slow or fast, but we'd still get out and we'd still be able to continue our run. Oh, my bad. Sorry.
Any questions? It's a lot of hands, I'm sure, but yeah.
You go back to the slide on the spring. The spring seal wheel.
With the what?
The spring seal wheel. Oh, yeah. So I guess my main concern with that is that, at least the way I conceptualize it, you might not get like the same compliant behavior at our size. You know, like all the literature out there on spring steel mesh wheels is for like far larger rovers, like the wind rowing vehicle. And that was essentially used to transport people during the Apollo era. So humans, and our rover is obviously way smaller. So in a smaller rover, we weigh far less. So our mesh, the way I see it, would be too stiff relative to this. And I don't see a way to compensate for that without losing the structural integrity, like making like the wires smaller, the wires thinner.
That would depend heavily on the material used, which would have to be kind of more experimented with, but that's a good point.
Can I ask you?
Yeah.
So John, I know this is your baby. So are these, you were using the word spring, so are these leaflets of steel that are like almost like meshed together, or are they springs?
Yeah, so current idea is like you would buy some like 32nd inch, some like very thin spring steel sheet from like MasterCard. It's formable. And you'd cut them and then you would bend them on like an arbor press, for example. We don't have the specifics labeled out, but we did a little bit of preliminary analysis and it seems like we have access to a furnace here at Purdue, or a few. I haven't figured out the size yet of that furnace, by the way. I should definitely send that message and ask.
Is the spring steel the name of the composite? It's called spring steel, or is are you just using?
It wouldn't be a composite, it'd be just like spring steel sheet from, composites are a second idea where we would maybe have some kind of composite leaflet where we layer on top to form the shape.
So is that like more like ductile or brittle, or like, what does it act like when it's like dented? Like if that were to run over a rock, would it just collapse?
For spring steel or for
For spring steel, I guess, because this wheel design, I feel like it's more of a materials engineering.
Oh yeah, absolutely it is. Sorry, I'm breathing into the mic. I'm so sorry. Yeah, so we don't actually know that yet. That's obviously like a very big thing. Like you're using this very thin spring steel for your compliance, but it's thin and it may get punctured. You go over a rock. We don't know that yet. So
Okay. I think especially like if you want to look at like past literature, like you're referring to, they use like something called SMA, which is like sheet memory alloy.
Yeah.
And that's like an extremely hard material to get a hold of. Like you said, it's tempered at a certain temperature so that it only like deforms once it hits that temperature. Any other temperature will bounce back. I think it's like, I would love for this to happen. It would probably be really expensive. I think it's worth it to talk to some materials engineers and consult them on that.
yeah.
I do think I liked your angled browser idea. If we were to sub that into the current field design, like something like that, but with angled browsers, like obviously that's the safe bet.
Which one? The rigid diagonal or the
I just remember it being said that angled browsers are they won against box browsers, yet like angled browsers seem to be the best option. If that would be like subbed in on our current build design, I think that would be like the safest bet. But obviously like this would be a cool side project. And then on another note, I had a question about the skid plate. So for 3D printing, like, would that just be like 100% infill on a giant print bed, or
No.
like, how would that?
100% infill, definitely not, but I'll let you talk more about it if you want to.
Sure. Preferably we wouldn't print out like a whole skid plate because there wouldn't be a big enough 3D printer that we find. So we would probably CAD the model and then split it up into smaller pieces, and then at the end we would just bolt them all together.
Yeah, because my understanding was we got stuck on a rock last year because it just got in between like one of our motors, and essentially like our drivetrain was exposed on the bottom. And to my knowledge, I just thought filling in was just like a floor or a ceiling instead of some sort of pot belly. Because I see us going full speed into a rock and the pot belly just denting and the whole robot tipping forward.
Yeah.
Like, and so I just thought covering the motors and making it one solid flat plane on the bottom would be better with obviously larger wheels that, it just can't get stuck if it's flat completely. I see almost like a concave down causing more issues than just a completely flat bottom on drivetrain.
That's a great point.
But we can test that, but.
So last year we did do just a flat skid plate on the bottom, and I'm pretty sure that's what it got caught on.
Yeah, it was it was hard to tell if it was stuck between excavation skid plate, the chain guard, or if it got onto the other side of chain guard. We think it got onto the other side of the chain guard and it was on the skid plate and there was a height difference between those.
Okay, so just making it like a continuous flat.
Yeah, that could work as well.
And then really quickly, I loved all the dust mitigation efforts. I think dust mitigation is very much like an excavation and deposition issue because we're literally throwing dust into the air. I do think it's really good to want to clean off wheels and certain parts of drivetrain. I do think a brush against the wheel, if anything, will cause more dust to go in the air. Wheels are meant to be dirty. It's okay if they're not cleaned off. I do think it's good. The chain, protecting the chain last year was a really good effort, but I do think we can use a lot of that brain power for dust mitigation within the other sub-teams, not necessarily drivetrain.
Yeah, and for dust mitigation, what we noticed last year was when we took one of the chain guards off, we then poured it out into a little pile with all the regolith inside of it. So it was mainly trying to prevent that. And that was mainly caused by how our chain tensioner was in there. So these ideas, depending on the design for other parts of the chain guard, could be used.
I think it's great effort, but usually it's active dust mitigation in terms of how the robot is performing in there. Now we're just kicking up so much dust with our excavation system. And we need to work on that. But I think you guys have good efforts, but it might be a little bit over-engineered to a certain point.
Peter, you
I
have
have
your
a lot of
hand
questions.
raised. I know.
First thing, go back to the chain versus shaft translation, please. Why is shaft being given such a lower power? Is that power transmission ability?
I believe the reason that we ended up giving shaft a much lower power score, I think that's just the way it ended up weighted, but our reasoning was that the power conversion from the gearbox to the shaft and then through the multiple bevel gears that takes you to the front wheel and then down the shaft and then the bevel gears to the back wheel wasn't as efficient as the chain.
Okay, so power is more of a power efficiency.
Yeah, we should have changed the name of that. It's more of an
Because
efficiency thing.
certainly, so have there been any sort of calculations or thought about that, or is that just sort of
Not really. That was mostly preliminary research into the efficiency of the chain versus the shaft. The chain has efficiency of 95 to 98%, whereas the shaft has 90 to 95% efficiency based on our research. So,
I think I was seeing smaller values for chain efficiency and shank when I was looking for last year, but I trust you. Because certainly, seeing that, I thought that was power transmission ability, and certainly drive shafts can transmit enough power. I mean, certainly they're doing more than we're doing.
I think cars don't want to deal with master links.
yeah, I think it mostly just came down to weight and the ease of implementation, because doing a shaft would be we'd have to be really specific about everything, and then once we had it on, it'd be really hard to change things to something.
Did you guys not look at belt this year?
We did not look at belt. Belt was we looked at last year. Yeah.
Okay, and now I'm talking about skid plates. So we've got a bunch of different designs that we're talking about here. They're all pretty geometrically complex. I'm wondering why. So the theory of having sort of a convex plate at the bottom, it makes sense to me in terms of trying to tip it. I don't see why just a straight pyramidal triangular pointed skid plate wouldn't work. I don't see why we need this rounded bottom. And that would certainly be much easier to make in terms of putting it on, putting a piece of metal on a bend and bending it, right?
Yeah, so I think personally, from what I think about it, when you have a pyramid type shape, if you get beached on a rock, it won't create enough tilt, and you would kind of just get stuck on it. So if you're here, I don't know, and the rock is here, it tilts a little bit, but with the round, it kind of creates momentum. I don't know how to explain it very well, but it it creates a little bit of momentum that can like help like
Okay.
if it goes
So-
up on
so-
it, then
So
it
you're
feels better.
basically thinking that the gradient is sort of, that sort of, gradiently, we can get to a higher slope at certain points, right? And like you'll start basically flat, and then the gradient will transition into being sort of more. Because to me, it feels like the point of the skid plate is more so that it will just, that if we're on a rock, the skid plate will cause the robot to be now sort of at a weird angle and slide off to one side, is sort of what it feels like to me.
That is kind of what we're going for, because if we get beached on a rock, we preferably want at least one side to be like on the regolith so that it can provide a little bit of traction.
Yeah.
So like even if it like we get off in like it takes like 3-5 minutes just to get off of that, we'll still be able to continue the run rather than just getting completely beached and not being able to move.
We all remember last year. And so that, well, I think that effect could be achieved sort of approximating a curve with just pieces that have like a couple of bends, right? Or like two pieces with shallower bends that we pull them together. I think there are ways that we can get around this that don't involve trying to essentially make our own like forming tools.
Oh yeah, definitely. There's definitely.
And then also, is there any idea of trying to make an asymmetrical design for this?
I haven't personally thought about it, but it could work. Although
Because I'm imagining, right, if we say that actually we always wanted to fall to this side, right, we just sort of decide that, I feel like we could come up with some asymmetrical design, maybe the whole thing is just sloped to one edge or something like that. I think that it's possible that we could be able to sort of make a more effective thing. I haven't thought about that much, just something to throw out there. Now let's get to wheels. Yeah, oh.
So, skid plate real quick. My concern with having any skid plate that's rounded or anything like that is that then at that point we're reducing our block clearance. Because we've seen over the past few years where we're getting into a crater and we're able to drive out, but only because we have that space in between the wheels that kind of go over the curve. If we have a skid plate that's rounded, it's just hit that like top edge of the crater, and I fear that we may not be able to get out of it.
I'm assuming these are over dramatized drawings, like the slope won't.
yes, it probably won't be like this deep. It'll probably be a lot shallower.
Yeah.
But yeah.
And then if it's shallower, then I think the shallower it gets, the more I think a slope can be better approximated by just a single point, right?
Yes.
Was there anything else? Okay, talking about wheels then. Okay.
When we're thinking about the shaft versus chain, can somebody explain the shaft a little bit more in depth? I don't think I understand.
So what we were thinking for shaft design would be you have the motor on a axle powering a gear onto another gear, which would then rotate a shaft to power the front wheels. And then going into the problems with that is we still need two shafts on both sides. And then if we were also doing the mini robot, it would be 4 shafts, and the assembly would take much longer than putting a bike chain on it. And then additionally, the gears, we thought about different types of gears, whether we just do a 90-degree gearbox to avoid having to assemble it, or just using different types of gears, such as a worm gear or 2 differential gears. And the problem with that is the worm gears are bad at translating the power, and then differential gears can wear out easily from the torque, so that's why.
Okay, so now I fully understand this. With a lot of robotics that's going on now, each wheel is its own module. So is it like a constraint to motors where we can't have a motor on each wheel, or have a motor pod for each wheel or something like that?
Weight, power, and cost. Yep.
Also,
in addition, we've had motors in every wheel in the past, and there was no benefit to it for us.
Yeah, the main issue with the multiple motors is we initially get problems with each of the motors were varying levels of good. So it was a lot of different powering, and also, as mentioned before, cost, weight, and it would also just be extra strain on P&H because they'd have more motors to plug into their thing. So minimizing the motors just as a weight thing. It is possible, we just switched off of it.
I think another note on that is that that's mostly beneficial if you're gonna be trying to do something like swerve drive, right? Where each of the motors, which would certainly improve our maneuverability, but that's also a lot more design work and efficiency, and we've seen it done on a much lighter robot before.
And usually it was suspension. It's like, I think it was like a rock coaster.
I don't recall WPI, I thought WPI just had great swerve drive. But, you know, if that's sort of not a route you're going down, if the wheels aren't moving, then there's really not typically a benefit to having four versus just having two and connecting them. Okay, can I talk about the wheels now?
Alex.
Yeah, think about skid plate.
So about skid plate, how do you evaluate skid plate effectiveness? What is your metric for test if you will say, hey, we determined that flat is good enough, or that we need one bend, we need infinite bend, this thing. How do you determine which one is best?
Yeah, so that'll mainly be if it can get off the rocks effectively, which is time mainly, and then how much weight does it add versus like a flat one. So if it ends up being like kind of flat with one bend in the middle, that's very similar to a flat skid plate. But we will definitely be doing a type of skid plate. It's just the shape of it, and then we'll be looking at how well it could get off of rocks or out of ditches, which we kind of forgot about, I'll be honest, because we didn't get stuck in a ditch last year.
And are you concerned about durability? Because if you're making it thin enough that it's light and not adding many kilograms of mass, it's also not very strong. So are you concerned about being heroic resting on it and then denting it, and then at that point you have to?
Yeah, so that kind of depends on material, which depends on design. So if we go for the one that's very similar to flat with a single bend, we could make that out of like a sheet of metal or acrylic, whatever. If we go for something that has more curves, it'll probably have to be 3D printed, like pot belly would be 3D printed. Something that's more wavy, like the bottom right one, that could be bent. But it's likely that it'll be made out of a sheet. And for that, it'll probably be like acrylic.
Kyle, what have you got?
I have things about shaft and skid plate.
Okay, we'll go with Kyle.
Let's start here.
So chain or shaft? I'm wondering with your trade study here, why is the ease of use for shaft below chain?
That's so wrong.
Because my understanding with chains in the past, with the tensioner, that is a massive point of failure for us. And just putting together a chain is gross. So with a shaft that's fixed distance, you don't have to worry about that tensioning. And so if I would almost think that chain and shaft should have their ease of use flipped, which that would be a 20-point swing putting shaft higher than chain in this trade study.
So we try to factor in an assembly for this part because to like make a shaft, it would be really hard to like change out the gearboxes, for example, without having to like disassemble a majority of the robots that just take wheels off. And then you also have to open up the gearboxes somehow. And then so with chain, it's easier because all you have to do is take off the dust cover for it. And then we also know what went wrong last year. So we have plans this year for multiple different chain tensioners, and that's more of a PDR thing.
Kyle, I'd also say that the pain of tensioners is perhaps counterbalanced by the pain of making 90-degree gearboxes.
Yes.
I mean, yeah, but you could also just get a worm wheel box, which is.
They discussed worm gearboxes and that it would work well. You can go more into that.
Basically, like worm gears are really poor efficiency in converting the power from the motor onto the shaft. And it's mostly just power efficiency. It's kind of not viable really to do worm gears.
My experiences with worm gearboxes as well is that they get munched very quickly and get turned into powder.
And yeah, and they shear.
Yes.
Very easily.
Okay, is it real time? Oh.
and skid plate, it's kind of in a similar vein to Sophia, where how is this curvature a benefit over a flat plate that just prevents the pinch points? Because what I see with the curvature is that you're introducing more pinch points and decreasing your ground clearance and making it easier to get beached on rocks. So is that risk of being easier to get beached better and like having the potential to get off better than having that more ground clearance, which makes it less likely to get beached, has less pinch points where it can get jammed? Just, I don't see why having such a complex skid plate design is beneficial.
Well, if we go with any design that like just comes out from the bottom, it will like prevent us, if we do run into a rock or some obstacle, we will end up like, I assume the robot would stop. I don't know exactly, but assuming it would run into it and the rock wouldn't go all the way underneath the robot. And at that point, if we had a flat skid plate, the rock would be under, and there's a possibility that it could just be launched up, or not launched, but like tilted up, or like fully just sitting on that rock, and then we can't do anything about it. But if we had some type of curvature under the robot, at least we could run into it. Maybe the robot realizes we can't go that way, and then it backs up and then goes another way. Instead, if it doesn't, and it just keeps going on the rock, it'll create momentum to tilt the robot back down onto its wheels and keep going.
I don't see where you're getting this extra momentum from, other than just you have to be stopped and you're relying on the fact that gravity is able to rotate you. Which, if you're beached, you're already kind of out of that one.
I mean, this is something you guys can play with once the robot's manufactured as well.
Yeah,
Like, it's not super complex in terms of like
No.
changing your design.
No, as long as the connection points are the same, it wouldn't be hard to interchange the design. I think the thinking with having it being curvature, the momentum is coming from being able to shift things in the robot, such as if bucket elevator is done, being able to lift or lower, that shifts your weight, and then that can give more momentum. Whereas if it's flat, it gives a little bit, but if it's curved, it can kind of get the ball rolling.
I don't think that changes the momentum in such a way that will allow you to tilt left or right, which is the direction that you will need to generally get unhinged in this case. That just moves your center mass forward and backwards reasonably.
Which could give the wheels more traction.
It's something you can test.
Yes.
I think you're
Yeah. It can be tested later. And for PDR, we'll have a better idea of what the design will look like as well. Like how low the curvature is, the slope, everything like that.
This is something that, having something that isn't just a flat plate, definitely will need to do a lot of testing, probably with just pure 3D printed models and smaller versions of the robot. That, I would say, you need to do a lot of looking into that. Because my gut feel is that this, having a curved plate, it is significantly, maybe having what Peter's proposed of flat plates might have some benefit, but in general, I think it would just be better to not have material there so you don't get beached on the rock in the first place than.
I don't think the skid plate's what's causing it to get beached on the rock.
Getting beached means that you are.
Or in a hole. Yeah.
If you are using the skid plate for its intended purpose, you are by definition beached here. Right? Just because it means that you have wheels off the ground.
Yes.
So I'm concerned that this will be an avenue that you learn that, oh, it's better to just not have material there to get beached on. But it's definitely something that you should look into.
You guys can test on there.
Yeah, we can test that. All right.
Okay.
Your
now I
tirade.
have a question for the wheels.
Yep.
Looking at the wheels, my first question, talking about the efficiency term in the trade study,
Yes.
right? That,
I'm
so
so
you're
sorry.
saying efficiency, that's not, are there any sort of calculations that are involved in trying to evaluate these designs, or is that more sort of a gut feel?
Okay, so efficiency, like we're measuring this as rolling resistance, so this is just pure like going straight forward. And so the gut feeling, if you've seen our trade study here, the reason that the compliant wheels have a higher efficiency than the non-compliant ones is because the idea is that in a situation where you have a soft surface, the majority of your rolling resistance comes from how much your wheels sink into the ground. It's completely unlike a rigid surface where you have you want your wheel to be as rigid as possible and the surface to be as rigid as possible to minimize rolling efficiency. That's why trains exist, for example. In soft terrain, it's almost the opposite. Almost, not quite. There's such a thing. It seems like there's such a thing as too much compliance, and the very little research I've done so far, by the way, this is mostly intuition. I want to be clear. But it seems like in order to decrease rolling resistance, the name of the game is to reduce how much your wheels sink. And if your wheels can distribute their load over a greater area, you decrease pressure and you decrease sinkage, and so you increase efficiency.
Okay, I follow you on that. My second question is just sort of in general, talking about different wheel designs. Are there any tools or processes that you think would be crucial for us to acquire the ability to do? Like, for example, if you're trying to do the compliant diagonal grounds, I should think that a rim roller might be incredibly important for making that out of rim, right?
Mm-hmm.
Or is there anything like that?
So just in general tooling for all the compliance stuff, my general understanding of how you get that compliance so far is you have some kind of stiff and high strength material. And so that looks like spring steel or that looks like composite parts generally. And so composites are super scary. I don't think that's something that maybe we should consider pursuing right now unless somebody has something else to say about that. But spring steel, the manufacturing for that looks like a furnace and it looks like a press. You buy the sheet metal and it's already formable, and then you press it into shape and you harden it and you quickly cool it in some oil or water, and then you temper it at a lower temperature, and then you have your part. That's my understanding of it right now, but if that's, I know Andrew, it's
sorry.
So I don't know why this just occurred, but the whole thing of heat tempering the spring steel and stuff, isn't that just sort of make it harder and therefore making it not compliant?
My understanding about the tempering part is making it harder, yeah. And then more steps so it doesn't break. Once again, I want to be very clear, I do not have very much knowledge about this at all. So seriously.
So my understanding of heat treatment and hardening is that is mostly a surface treatment to make the surfaces harder. But I don't know that it messes with the ductility. Well, messing with the ductility, it makes it more brittle, right? Which is why you then anneal it again, right? To introduce some of that ductility back into the materials. But talking about that, do you know anything about the heat treatment process in terms of is this the kind of heat treatment process where we're going to need to quench it, or is this just an annealing process?
It seems I know Aridin looked into this a lot. I can see you shaking. Yeah, absolutely. Please do. Aridin looked into this a lot last year for anybody new here. She's the one who came up with that CAD. So she looked into this a lot.
Yeah. Thank you. So basically, it would be a quenching process, and I've been talking to some people with Puma because they have a blacksmithing facility a little ways past Lilly. Where they have a bladesmithing section as well, so they have the ability to temper and they have quenching oil, everything that we would need. And because they're also a student organization, they'd be not very difficult to I'm also a member anyway, so I can just talk to them and be like, hey, can you teach me? Or hey, can we work together on this? In terms of hardening, yes, it does increase brittleness, hardness, everything, but annealed spring steel is actually quite soft, which is why we'd want to buy it annealed anyway, so that it's soft enough we could basically hand form it or manually press it into shape. And then we would harden it to bring back a lot of that elasticity.
Yeah.
But make it more brittle, but it increases the overall yield strength, to my knowledge.
Yes.
The yield strength?
Well, if you're maybe a mechanical.
Yeah, well, it's inherent when you harden a material, you increase yield strength, but also brittleness as well, especially for metals. Yeah.
I got another question about the spring steel mesh wheels.
Yeah.
I mean, obviously, it's still very early on. You just had last year, right?
Mm-hmm.
So with the configuration, I think John called it leaflets.
Yeah.
Spring steel. I think in most implementations, they use like a fiber wire mesh.
Mhm.
From my understanding, it's the weave of the wires that creates like a system that allows for greater stretch distribution. So do you think having these leaflets would still result in compliant behavior?
Yeah.
Concerns about like side to side, like. would it
Yeah. So the main reason I designed it like this was because mesh is simply not within our scope of manufacturability. So by designing it this way, where I can start with a flat piece of sheet metal and cut out leaflets, bend them into shape, and then introduce elasticity. It was simply for manufacturability, but we can also control how thick the sheet metal is and therefore control the compliance that way. We can also, there's a range of like tempering temperatures that can affect the properties of the material as well. So we can also control it that way.
Yeah, I guess my main thing was that like it's not mesh.
Mhm.
Combined with the fact that our rover is light compared to stuff in literature.
Yeah.
It wouldn't really be compliant.
Yeah.
That's a good point. We can take the actual leaflets.
Yeah. I haven't calculated, like deflection for the thinnest, sheet metal that I could find. But just based on like, if I wanted 10% deflection, it would recommend 2 millimeters of thickness. Yeah. So we definitely have room to play.
One note on that is that Googling just now, I found like 10 or 12 different companies that will sell you a spring steel wire mesh.
Yeah,
So,
we probably need like a hydraulic press though.
Yeah.
Getting that inside, we need the steps of like probably hours.
Yeah.
Right, so that's like a whole other
Yeah.
level of.
yeah.
compliance.
Just try to get,
This-
huh?
At least from what I've read, that like you want it weaved in a particular way.
This-
You just roll them into each other, but yeah, I worked on those wheels, so that's why I know about it, but.
This was discussed last year, and for the wire mesh, it was determined that that is far outside of our manufacturing scope for this year, next year, and maybe probably future years, unless Bechtel has a very big renovation, which they probably won't. So wire mesh is not a good design. That's why it went towards the leaflet.
I like this design, I think the discussion on this will probably happen later.
Yeah, talking more about moving on to other things. So right now you have one design which is based on other teams' other teams' wheels from last year, right? Is this because this is the wheel that you saw as working the best, or the team that had the best maneuverability? I seem to see that a number of teams seem to be able to turn better than us.
Oh yeah, so to be clear, like our wheel last year, this box grouser, if you go back to you can see like the mobility is, these are grouser designs. Like our mobility is like 0 basically for box grousers. Like it's actually the worst possible, you can't imagine a worse one, right? It's just like a big fat face turning. No, it was definitely pretty bad. There were some not properly made conclusions after during PDR that should have been shot down.
Still step forward, we tried it.
It was very, very small step forward and a few steps back in other areas, but
I'm very proud of the work you did. That was very good.
it looks cool. It looks really cool. I love this photo. It's on the resume, to be clear. Okay, it's on the resume.
I will say
Front and center.
that last year there was a team that had 3 metal casted wheels and they reached every run. So I can't say I can get something worse.
Yeah, that's true. MSOE was struggling out there.
So looking at the rigid diagonal grouser, right?
Yeah.
So is that sort of your estimation of the cream of the crop in terms of sourcing ideas from other teams?
Yeah, so that was from Utah, and I feel like you want to speak on that.
Yes, we also looked at a bunch of the other teams who also had really good turning, and one of the common factors we saw was angled grousers. And if you orient the wheel where it almost forms like a diamond with like the angle of each grouser, it creates a really good point turning kind of radius compared to our.
And then I guess my final question is, it seems like there's a lot of sort of question marks in all of this wheel design process, right? Is there any plan to try to set up some form of testing or testing and sort of actually?
We don't have a pit at the moment.
Give it 3 weeks. What, you're testing right today? Calm down.
I can speak on that. Okay. So in regards to testing, like we definitely want to measure each one of these criteria. Unfortunately, maybe be in a sand pit instead of the regular pit. Our plan on measuring each of them is kind of in the description a bit. So like mobility, like we're basically planning on like making a scale model as large as we can of each, and then getting like a scale and like pulling it and seeing how much force we get laterally when it's slipping. And traction is like, pulling it the other direction without it slipping and all that. They'll probably be 3D printed, yeah. And then I'm not entirely sure how we're gonna mimic the compliance wheels because like.
It could be a long-term project. I mean, clients feel like, yes, it's still, you have enough to have.
I feel like we keep on saying that though, like every year, like it's always a next year thing, I mean, at some point we gotta actually commit.
I'd be seriously concerned about it deforming permanently when the robot sits
Yeah.
idle, it just gets flat on the bottom, that's my main.
I know NASA had on their lunar rover wheels, they had a bar like inside the wheel to prevent it from permanently deforming, and we would probably have that anyway for the angle grouser attachment.
It's up to the chief engineer if you want to
Yeah.
take that risk.
Yeah,
I think-
Like two mesh, one was rigid,
Mhm.
one was like compliant.
Yeah.
So that if the compliant mesh, the compliant wheel went over a rock that was really big.
Yeah,
It would hit that rigid.
Yeah.
area, and it would just go on top.
I also want to note that like we could maybe like look into both from PDR to SDR, and then I'm sorry, from SDR to PDR, we could like prototype both and see the feasibility because rigid diagonal grouser, like we know we can make that really easily. And if we commit a lot of time to these compliant wheels, the final product of the rigid diagonal probably will not be as well optimized. You might be looking at a little bit poor efficiency and mobility, because maybe we won't have time to do some other tests. But I mean, in my opinion, I think that's worth it for sure.
If we do two robots, I don't think it would.
Oh yeah, that's the other thing. I didn't bring that up, but two robot, like, why would you need a compliant wheel on your excavation robot? You'd probably be looking at lowering weight instead because it's not going over that versatile terrain, and then it looks like we're having tracks on the mini bot. So the compliant wheels would be definitely maybe over engineering that a bit. So. Got it. You had a question?
I was going to also say compliant wheels will take up a lot of time, both on the design and on the manufacturing side.
Yeah.
And looking at that diagram, I understand it's not a complete diagram, but there are several things that would be very hard to make in the compliant diagonal grouser.
Yeah.
Diagram. And the rigid diagonal, we know we can make it, we can spend time optimizing it as opposed to spending time. How do we even do this?
Mm-hmm.
So I would be very curious. And also, a lot of your ideas are much more like manufacturing, complex manufacturing side.
Yeah.
So be very careful with making sure that your ideas, that you don't spend too much time on making an idea that, well, this isn't great, but the only way we can do it is to do it like this in a suboptimal way, because otherwise it's physically impossible to make it.
Mm-hmm.
Versus on the rigid grouser, like, hey, in theory, this one is way worse, but we can make all the parts so it end up being a better version of itself and end up being better.
Yeah. It seems like it's just a matter of like you want to play it safe or not. And I mean, the way I see it is that you can do both because at least between SDR and PDR, you don't need a firm design, right? And it seems like we're able to pivot to rigid diagonal pretty easily in case we ever run into problems. Yeah.
I might be just misunderstanding the idea of compliance, but with a relationship between compliance and power efficiency, wouldn't a less compliant wheel be more power efficient? Because, for example, say a bike tire, like a less inflated bike tire would be more compliant than a more inflated bike tire, right?
Yeah.
And when you have a more inflated bike tire, it requires less force on the pedals to be able to move at the same speed. So, I guess, is this a bad analogy, or am I just completely misunderstanding?
No, I mean, it's different when it's a soft surface. That's the thing. So like bike tires and car tires and like trains, they're on very hard surfaces. But when your surface starts to like deform a lot, you start not caring so much about like how your wheel deforms, and more so about how the terrain deforms under you. And your rolling efficiency. I mean, I wish I read this book on terra mechanics, but honestly, ChatGPT just said that like, hear me out, okay? I'll look into a bit more in the book, all right? But okay, it seems like your rolling efficiency is like proportional to the cube of how much you sink. All right, that's the reference. All right, these models are wrong. All right, sometimes, but that's like basically just like showing the relationship that like you care a lot about how much your wheel sinks to the ground. It's also a big reason why like weight, like if we lower the weight of our robot, like not only are we decreasing the weight and scoring more points there, but we're also just straight up increasing our power efficiency. So weight is actually like double edge in that regard. Peter?
I have questions that aren't about the wheels.
Wait, I think we have one question up there. Yeah.
Maybe I don't know if I just can't see the picture very well, but like the wheels that that NASA's version of like the Moon Robotics type of robot makes, like Razor or something like that, their wheel looks very different in comparison to most of these. Like it doesn't have ribs that sit to the ground at all. It almost looks completely flat.
Yeah, so I think NASA's, oh man, I don't know. I forgot if I think it's perpendicular grousers. Does that have skid steer though? It's a big difference whether the robot has skid steer or independent turning.
The type of drivetrain system the robot has, so what we use is skid steer, that changes which wheels are effective very heavily. Whereas like if you're using, someone brought up swerve drive earlier, I think it was you. If you're using swerve drive, you have very different wheels than if you have skid steer. We're using skid steer, so we need to have wheels that reflect that, which makes it harder to look at other teams for their wheel design because it may look like they have very good wheel design, but it's only effective for their type of drive system.
And NASA contractors are also looking at what we call like hoop wheels. And it's like, it's a non-pneumatic, like it's a pneumatic wheel without rubber or pressurized air. And they're looking at like coatings, which create friction.
NASA contractors have millions of dollars.
I think you guys are in a very good spot for SDR. I think a lot of the discussion is starting to move in almost PDR type of talk.
Yes.
I think you have a great direction to move forward, and I like the work you've done so far. So I think it's probably about time to move on from wheels.
I want to go to lunch, Holden.
We're going to lunch at the end, right?
We're gonna do lunch after drivetrain now.
Yeah, does anybody have any more questions? Oh, done.
All right, Donna.
Oh, we got 4 questions.
I have a question about your dust tolerancing.
The what?
The flexible seal dust tolerancing.
Yeah.
What are you planning on doing material-wise for that?
The inner rings can be printed with TPU, or we can buy them online too.
How flexible is that? Because last year, me and Aaron were making some of the dust covers, and we had issues with them not going in or not coming out. That was really, okay, TPU is very, okay.
TPU is squishy. It depends on the infill, so you can actually change how squishy TPU is. I'm just gonna go straight down the line, so Alex is next.
We have questions about many product things, and that's.
Who doesn't have many hot questions?
Yeah.
Any one robot questions left? Peter?
Talking about the dust tolerance, first off, for the like electrostatically charging a plate, do we know what the method for doing that is?
That is a much more long-term project that is being looked at by VIP research.
Okay, and then for the dust covers, has there been any consideration of trying to use like a standard or semi-standard like rubber O-ring instead of the TPU printed, right? 'Cause
Yeah, that could be bought.
yeah, right. O-rings can be bought, and PLA is cheaper and very, very easy to print.
So there's different options for what material can be used to make them.
Yeah.
Whether we buy it or make it is a later decision, probably a PDR one. Hans?
So for the frame, I'm assuming you're going with box tube again?
Yes.
Okay. Then with the gearboxes, you also mentioned you're going to go with the box tube gearboxes. Can you
Yes.
provide some of the reasoning behind that?
Why we're still going with those?
Yes.
They worked very well, besides the one that got dimpled in when it was very aggressively put together due to issues with how they were assembled, which is why we are going to work on the design for those to make it easier to assemble, and then 3D print a test run basically for assembly. But structurally, they worked very well. So we're trying to continue with that, but make the ease of assembly there. But once we assembled them, because we went with chain, once they were assembled, we did not have to take them apart during competition. Whereas if we did shaft, we would have, if we had an issue with the shaft, we would have to take all of that apart and take those off the robot as well. Alex again.
One more thing I was thinking about that. Here you said you're doing one gearbox. I know that last year we wanted 201 gearboxes, but we didn't because they exploded repeatedly due to factors outside our control. Have you considered using a 2-to-1 gearbox inside drivetrains so we can get the same torque output out of a 50-to-1 gearbox?
That was not thought of, but it can be. That's not a huge design change with the gearbox, so that can be discussed further.
Because I looked into that last year, and that was not possible due to having the box tube gearboxes.
Okay.
It's just you're very limited by the size. You don't have very much space in there. And considering the metric shafts that we went with, if we wanted to have an affordable gear, and even those gears that we bought were like $50, if you want to have like a reasonably priced gear that is the correct tubing for the actual shaft and can fit in there, it either didn't exist or we had to make it ourselves.
Yeah, maybe something that's like, maybe we can't get 2-to-1, maybe like even like 1.25 or 1.5. Like, I don't know what the gear sizing is, but any amount would help because more torque is better.
That can be looked into.
Okay.
Yes.
In terms of assembling a frame, because typically frame is very bulk and fastener heavy.
Yes.
Have you thought at all about loading versus not loading? I have my own personal opinions on it. Let's see if you thought about it.
Well, so welding versus non-welding the frame, that.
I'm not on your team, I'm very against welding. I'm not really straight up about that, like, teams that have welded their frames have regretted it. It's like, I just.
Yeah, we did have to take apart the frame last year, but I feel like the second we weld it, we'll have to take it apart. So like I have my own personal opinions on that as well. Who would weld it? Probably you. So.
Make sure you weren't going to weld it. It's a stupid idea.
Yeah, I don't think we're looking at welding it. It would be a weight saving mechanism, but it would probably also have a lot of regrets attached to it. Yeah. All right. Cool. On to mini-bot questions. That's because we introduced an entirely new concept.
Oh, that's fair.
All right. Yep.
I don't know if I remember properly, but did you see you were gonna print the tread for mini bots?
Yes.
How are we gonna prevent stretch? Because I tried to print a belt out of TV before and it stretched like after, I would say like 30 minutes of using it to the point where you're supposed to use it.
Okay. That's good to know because a lot of what I have found online, the issues with printing with TPU were more that it could crack, depending on how it's printed. And that was mainly going to be trying to mitigate it with a tensioner system in the treads. So stretching could also be mitigated like that. We could change the design. If it needs to be, it could be shrunk. So then when it does stretch, it is to the correct dimensions. That'll probably have to be experimented with. If anyone has lots of experience printing with TPU, that would be helpful. Yeah.
Instead of 3D printing the belt, have you considered making the belt into an excavation gun where you can go and buy the belt and then go and add grounders or add stuff onto it with bolts?
Yeah, that was thought about. Adding grousers with bolts onto treads, and then also having the treads still be able to go around properly. I feel like it'd be very easy for something to get stuck. But that would kind of depend more on the design. Also, bolting in grousers is not the best.
My main concern is that if you want you need a very long single thread.
Yes.
So you need to get as one continuous single piece, otherwise that
yes.
You're not. So you need to go and wrap it up a bunch on a 3D printer, even then I'm not sure if I can fit on hours. Or you can find a larger printer, which is always a concern.
Yeah, finding a larger printer, I've kind of already done that. I've talked to the ME3D print lab. If it's less than 8 hours, which I don't think it will be, they would let us print there for free. If it is more than 8 hours, we can go to the 3D Print Club, and if we bring a roll of TPU, so we then pay for the TPU, we can use their printers to print it. And they have much larger build plates.
Yeah, my concern would be that if you're looking at what are the dimensions of the mini robot again that you had? So you're looking at a 29-inch long belt around, so you're looking at a 60 at least inch long belt.
Yeah.
That is a lot of folding.
Yes.
Are you concerned about that doing weird things structure?
Yes, so that was a concern. That's also why individual treads were looked at. So if it turns out where one tread just isn't feasible to print, then making individual treads would probably be the next go-to. Attaching grousers to the tread, again, I don't think it's the best go-to idea, but it could be looked at. That's more manufacturing. How would we make it, which will be looked at. That's a good idea. Yep.
A similar note on treads is, have we looked into more of a chain tread system where we have, there's just a chain link that have sort of tread flaps attached, because that's more of what actually exists in industry and what other teams have done in competition. Do you understand what I'm saying?
I think so.
So it's basically you have two big sprockets and there's a chain going around them, but there are actually flaps attached to each chain link.
Yeah.
Right, as they go around, and you can probably find chain links that will have sort of such an attachment mechanism, right? And then there are flaps attached to each of those chain links that go around.
To my understanding, that is very similar to how just treads in general work.
Right, exactly, but it means that we don't have a 3D printer.
I think the issue they have with that is you have to speak to request a specification in order for the just change to that.
Yes.
Yes.
But if we go with that, then we might as well just go with individual treads, because then we have more options for how we make them. Because the individual treads is basically just like chain links and then just little like poles.
Oh, that's what you're saying with that.
Yay.
One thing, just based on the pictures that you have at the bottom, that one of your design goals, it's more, what's the ground clearance gonna look like for this robot?
So that depends. The pictures shown are all for ones used like on dirt. So we would have very different ground clearances. It also depends on what deposition looks like. So for dump truck, we would be off. It depends on how high off the ground we need to be so that we can deposit into the berm zone repeatedly without having to climb up onto our own berm. Also, if we need to fit under the larger robot, then we would have to be much shorter. If we don't have to fit under the larger robot, we could get multiple inches of clearance. That also changes how long the tread would have to be.
I mean, I want to say just in general, getting underneath the robot, just what I'm thinking, that will not be possible to have a still functioning robot.
It's not likely for us to go that route. It was just unclear if it was when this trade study was done.
You can, if you look at something and say this is just, odds are it's not going to work, you can just tell the rest of your team that any option that requires this should not be looked at because we don't think it's possible. But because that, going underneath and having, in general, a low ground clearance setup seems like a really bad idea for this competition.
Yes, that's why we're not doing it.
It's more concerned that all of your mini bots.
That's why we're likely for drivetrain to be 8 inches tall total. About 5 of those will probably be clearance. Okay. Yes.
That is like bare minimum for what I would think for this competition. Okay.
Yes, it could get changed. Yep.
As far as the tread goes, is there anything stopping us from using pre-made tread from a different provider? I know in FRC they used to use tread a lot, not very well anymore, but there are a lot of resources and designs that have been used in the past, and they have pre-made tread of the actual tread of the rubber part. and it's really, really durable.
Yeah, so pre-made treads, the main issue, those are size constraints. We have very weird sizes compared to FRC, toy like treads, like for like tanks and stuff. We just have very different constraints than those. So if I was not able to find one when I was shopping around, that would fit what we need. If you are able to find one, please send me the link. But I was not able to find one that would fit because it also needs to have the grousers that'll allow us to move in Regulate, which most of them do not, just flat out.
I think that's what we found 2 years ago when we did it too, that we had the custom media.
Yeah. Yeah.
Yeah. So going back to the main slide of the mini robot. So you say that your golf drive supports 60 kilograms.
Yep.
And remembering back, both mini robots support 130 kilograms.
Yep.
So if main robot weighs 60 kilograms, that's 70 kilos of regular. And the mini robot weighs 20 kilos, that's 40 kilos of regular, which is almost half the amount.
Yeah, so how much weight it supports depends heavily on what material it's made out of. This was done on the lighter end of the scale. So minimum we want it to be able to support 60 kilograms. They're flipped.
Well, more in the sense of, I think that on the upper end of that, we're planning to do more than 60 kilograms regular for both.
Yes, and we can adjust for that.
Okay.
Yes, this is a very rough estimate for Minibot.
On that note, are you concerned, you mentioned 3D printing and durability, are you concerned that a 3D printed part might not have to go and put 60 to 100 kilos on top of it?
That's why material matters. Also for how much the robot weight, how much the Minibot weighs, and then how much weight it can carry. Those are very relevant parameters. Because the more the Minibot needs to carry, the more durable and heavy materials it needs to be made out of, which means the more it'll weigh. Where?
Kind of at this point,
Oh.
I get the feeling that there needs to be a meeting between the subsystems talking about the mini bot.
Yeah.
Like, because to me, it seems like there hasn't been that much communication between the drivetrain side and the software side and the excavation side. Excavation and software talks a bit, or excavation deposition software talks, but it sounds like drivetrain hasn't been that included in that, because having your weight be 5 kilograms for this, and your main robot is 20, I think, for drivetrain.
It depends on what the frame is made out of. Which, yes,
Why do they
so
have to support such different loads? Because excavation is 20 kilograms. If you're gonna support 60 kilograms of regular, your drivetrains can't be that different.
yeah, the estimate for how much weight it can support for the Minibot was not made as accurate as the main robot by accident. And it depends on what materials it's made out of. If we want to make it out of, steel rods supporting everything and like aluminum, then it'll be able to support a lot of weight. If we want to make it all out of plastic, it'll be very lightweight, but it won't be able to support a lot. So it depends, and we do need to talk more with other subsystems. I was mainly waiting on figuring out which deposition system was going to go on Mini Robot after this design review to then figure out how much weight it should be able to support.
I think that makes a pretty good break point. Drivetrain.
Yes, it's 12:45.
Yeah, we went a little over schedule with them. I know you might have some other questions. If so, you can talk to them afterwards.
Yep.
Thank you, Drivetrain, for that. Okay. Considering where we are in the day, we're going to take a 1 hour lunch and reconvene here at 1:45 with power and hardware, and then finish with software and systems.
Yeah, I think it's 90 minutes.
Now that I've presented, I want to hit up an EPC eventually. So, so that means my presentation goes up, then I can just go off.
Yeah, you're welcome to. You can also stay if you'd like to hear power and hardware software, but it's up to you.
Oh, I'm sorry, you guys.
I really kind of want to say, we had like 2.5 meetings, not even. 1.5 was meeting, it's like.
I wasn't even, it was like, yeah. It's like a conversation.
Yeah.
Like, so like, you should probably write some shit down, you know, just read all of this.
Lily, I didn't take it up.
Yeah. I think this needs to go on.
Me too.
It's gonna be a long day.
It's not. No, it was my friend mom that was doing some areas. I was like, oh. It's like, it was all, there was an all
Alright, I feel better. Dude, this is a public spot.
If you go to leave the first one, they kind of live here.
That's just how it is.
They kind of cool with it. I don't see anything laying on the food.
Are you your professor? Yeah, speakers, they connect to. Hey, yeah, Dan, you don't care, go back down there, go back here. I want you to say something, you said a normal public voice, I want to hear it this time.
You can definitely hear people even if you don't have a mic. It's really, yeah, as long as you speak loud. I have professors who don't speak very loud and it's impossible to hear them. But they usually have mics, they connect.
Oh, I see there's speakers.
Yeah, speakers up there.
Yeah, I think the acoustics is such.
This actually. Hello? 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 Testing. Hello, students.
I have a question, what's the universal solid, please?
It's, I believe it's water.
She's under break.
She's missing out.
She's not having fun like that, she doesn't know. We'll get on her. These are kind of things you can do Monday to Friday, Monday to Friday.
Is that some sort of surgery again? Why not? Why not? Why not the year ago?
I agree. Yeah, I think he's like, they have to bring it in. I think the president's probably, so she's like, and then they can do everything last minute. Yeah, like, that's what they go to the. But a lot of teams do that. I think they kind of give me a money so we can come up with teams on house.
Do Monday. Again.
I would not Schmidt the day of, because it would be cool. I like how we get Eastern or something.
Let's do Monday Eastern.
Yeah, and then people would be like, at midnight, they're like, oh my god, I thought it was 2, I had 11:59. Dude, tell me, it's like, it's like, get on it. And it was just not,
Yeah, I'm gonna sort of ask a stupid question. Sophia, I do have to say, the code is absolutely dripping. Yeah, absolutely. You're actually wonderful. No, it's actually great. Yeah. No. I mean, line of actually had digital heating and software in front of us.
They have to get that.
They did, right, they have a big thing. And it's still. They gave us a number. Yeah, I also.
Yes, if I are actually way too involved to the point of. I don't know how to. It is, like, if Alex has then but also like you look at their teams from the past year. I think I know the rest of that. But they make that so that's the first. Like, we literally look like hired actors.
I'm not able to see it.
No, she's not even.
So low.
Yeah.
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 It's not much.
Well, it's not actually worth it. Well, no, right, I didn't comment because I'm like, I know you guys are actually. Right, I know you guys are not gonna do this, but they were like, all these are really heavy and really expensive, and I'm like, we have a solution. There's a company that will sell us plastic all. It's an offense to me that you don't know that. We are all, why was why is SDR? No, in the here. Right? You only have 6 minutes to do that. Well, if you're talking to me, you don't make sense that more, there would have been less That's what they said, and that's crazy. What was your take home today? Big concern. I think it's back.
I need to make like this. I had those, and then I had to go through it on my computer.
Most of my stuff
Depending on how many.
Okay, I'll like. So hopefully on the design side, like, and then like I'll be on the. It is to have it where they bring.
No, it's like if you never run over a rock, you never have any problems.
No, it's like, if we run over a rock, yeah, or also, I think you don't have to run over. It is, I took my, you're like, oh, you want. That's like,
We're gonna transition.
Oh my God, like. People are cleaning up this today. And yet we still have a giant.
All right, welcome back, everyone. We're gonna get started here. We're gonna change up the schedule a little bit. We're gonna start with software instead of power and hardware. So if the software presenters could please come down and we'll start with them. And then we'll move to power and hardware after software.
Yes.
Hello. How are we doing after lunch? All right, awesome. So we're gonna get started with software. First things first, we wanted to go over kind of the system architecture, kind of go through the inputs and the overall outputs. So in the very top left, you can see kind of some system outputs. We're gonna go over our autonomy stack first. So essentially, we start with our depth cameras and LiDAR, which are our main sensing instruments. And these give us image data and point clouds, which we can use for April tag processing, which gives us a global estimate of our position. Because when we start our autonomy run, our robot has no idea of knowing where it is. So the April tag kind of gives us a global position. The point clouds and the RGB data work together to give us obstacle detection as well, which inform our kind of mapping of where obstacles are in a 3D space. They also help us do localization through a process called SLAM, simultaneous localization and mapping, which gives us our position to an accurate degree. So once we've computed our obstacles and our position, we feed the position into a behavior state machine, which is essentially our centralized planning structure. Think of it as kind of like the engineering management of our software scheme. It tells the robot what to do, when to do it. So the position goes into the behavior state machine, which is responsible for saying, okay, it's time to traverse to our excavation zone, or it's time to start mining, or it's time to start depositing, which gives the planner a goal. From this goal, the planner creates a path to follow using the obstacle map that's generated by our detection scheme, and then feeds it into our path follower to actually get from point A to point B. So the path follower publishes our actual velocities, which gets interpreted by our drive controller and our motor control firmware to get turned into actual motor controls, which is our main system output. From our firmware as well, we also get sensor data, which informs our behavior scheme in case of stalls. So for example, if the firmware says that there's a torque spike, which we found as indicative as stalling, it'll tell behavior, hey, you need to perform the operations to manually reset the motor and then start again. So that's kind of what the autonomy scheme looks like. The behavior also controls the excavation deposition controller, so controls the bucket elevator and the deposition conveyor belt that we had last year. And so that's pretty much all of what autonomy is doing. From teleoperated, it's a lot more simple. It's essentially just takes a manual control, converts it to directly into motor commands, and then sends it through the firmware.
Yeah, so perception-wise, we are planning, we want to have, compared to last year, we want to have better coverage of our environment. Last year, we had 2 cameras, but we still weren't able to see everything around us. So we want to be able to have more FOV on the front of our robot to be able to see obstacles that we might turn towards in the future. That we ended up hitting in KSC Run 2 last year was because we turned into an obstacle that we hadn't seen previously. That might be achieved through a use of a 3D LiDAR in the front, which will have a very wide FOV, or more depth cameras, like you can see in that image on the right, placed such that you could have a better wide angle. Also, placing them up higher and more angled would be good. We'll have to talk to deposition, excavation, and drivetrain to figure out where mounting points will go for that and talk about that later.
So one thing that we're gonna kind of look at is more accurate positioning and obstacle maps specifically. So one thing that we struggled with at competition was accurately detecting certain obstacles. For example, we struggled a little bit with craters. There were a few rocks that just seemed too small for our detection system to be able to find and map in a 3D space. So one thing that we're gonna be looking at, or a couple things. First and foremost, we're gonna be trying to utilize LiDAR. So one thing that we've noticed from depth cameras is while they're really good for shorter distances, they tend to be under kind of restrained by their noise in the images. So that can end up throwing things off and give us some outliers. So for example, in our first round at KSC, we had an outlier that prevented our autonomous traversal, which ended up cutting down drastically the number of points we could have scored in that autonomous run. In addition to utilizing LiDAR for kind of more accurate point clouds and for more accurate 3D understanding, we also are trying to develop some machine learning methods for the obstacle detection and obstacle segmentation based on our point clouds and based off of our images. So the idea behind this is that kind of in these images, you can see the rocks in that RGB image. And so It's very like visual features, which is something that a machine learning algorithm can learn and can distinguish between. So we're hoping that if we implement machine learning methods as opposed to just our pure point cloud processing methods, we can achieve a higher degree of certainty of where rocks are with a higher accuracy. In addition to this, we're also trying to do more crater detection and boundary identification. So whenever we detect a crater, we're really good at seeing the backs of the crater, but not very good at noticing like the absolute bounds of it. So you can see in the bottom left image, that's what our point cloud looks like whenever we detect a crater. That area in the back is just the back wall of the crater, whereas there's a big empty space at the bottom there. So what ends up happening in our algorithm is it does all the processing on that back part without really processing the front part, which ends up in us going into a crater a lot of the time. So this year we want to do better in terms of identifying the boundary of that crater and planning around that instead, as opposed to just like the low points in that crater that we detect. And all of this would feed into a custom cost map. So essentially, up until this point, we've been using an off-the-shelf cost map that's generated by our positioning algorithm, which we found to be sometimes slow and also only using the point cloud processing. So for more accuracy and for a faster refresh rate, we're also going to be working on a custom path planning cost map.
Next, talk about path planning. We want to create better paths. Right now, the way that we're planning is that we're doing the shortest possible path in terms of distance, which you can see on the left. Well, this is not the most optimal because it takes time for us to start turning and actually turn versus moving straight. So something like on the right where you're moving in straight lines as much as possible would be a more optimal path. So working on different path planners to make that happen. Also looking at, as you said, cost map, being able to go further away from obstacles when necessary, but still being able to take the tight gaps if we must do that based off the layout of the arena. And then looking at some other planners that aren't grid-based. Right now, everything has to be north, south, east, west. It can't go in the diagonal very efficiently. So I'm looking at a different planner that could be able to do that too.
So in addition to path planning, we have to have a good way of executing on that plan. So we had some really good steps this past year with our implementation of point-to-point, which worked really well in competition. However, it was kind of time expensive. There was a lot of stopping, a lot of turning. There were a few points where we had a little bit of indecisive moments where we just kind of like spin one direction and then another in place. So one thing that we do want to look into and kind of tune are some other controllers. Obviously, this will have to depend on what the wheel design ends up being and how the dynamics of that work out. But we're hoping that we'll have the opportunity to do kind of smoother spline-based methods for a more optimal trajectory so that we can get more cycles in. And that would include pure pursuit, which we started development on already, and potentially reinvestigating MPPI from a few years ago. Because the algorithm is sound, it was just the wheel dynamics that ended up kind of being the killer there. We also want to kind of do a little bit more in terms of point-to-point. So we want to make fewer point turns to decrease our ground deformation. I believe in one of our first runs at UCF, what ended up happening is we were kind of indecisive and we had a lot of point turns that ended up causing a crater in and of itself, and the robot thought that it was in a crater when it really wasn't, essentially stopping our planning. So we want to make sure that we're not really, we want to take deformation of the arena into account so we don't mess up our own path followers and obstacle detection, because this year especially with the longer distance between the excavation zone and the deposition zone, we need to make sure that traversal is consistent all the time. So another thing that we want to improve is behavior. So one thing that we have to improve for behavior is we need to adjust for the new layout. So now after we excavate, we need to plan to the deposition zone and then deposit there and then plan back to the excavation zone. So we need to change that plan a little bit and also investigate how this works with a 2-robot system. What it might end up being is we might have kind of 2 state machines, one for the main robot, one for the smaller robot, but essentially doing more research into the state machine system. And the reason, kind of an overview of what a state machine system would entail is essentially like abstracting everything that the robot does. Is essentially, so excavation has a bunch of actions associated with it. Deposition has a bunch of actions associated with it. And these actions are only triggered by going to that state. So essentially, this makes it really easy to insert a new, like a new error into there and say, okay, if we're excavating and we get like a stall message, then we can change our state to stalled and then carry out the actions that are associated with that, and then re-enter our behavior flow really, really easily. So it makes things really easier, a lot easier for error handling and recovery.
Another thing that we're looking at this year is having a separate compute box, separate from the P&H box. This would be a second box that would only have software components. It would operate off of a separate battery from the main robot battery, which is allowed by the rules of having a smaller battery that would only power the laptop computer. It would not go through the power meter or e-stop, which will help us significantly when we want reducing power consumption. And it would make sure that if we hit e-stop, we can still communicate with the robot after that. And this also allows for just better organization within the P&H box and more flexibility for us in the compute box, because P&H has a lot of components that they have to decide on pretty early, and they have to have a lot of wires in their system, which means that they have a lot more organization that they need to do. Whereas we have a lot of different options that we can take, and depending on how things perform later in the semester and when we actually get to testing the robot, we may need to switch things out very somewhat often. So we need to have a bit more flexibility in what we can do. So the responsibility for design and layout will be on software, and then we'll work with P&H for the connection points and any wires that need to communicate across. And this is a small, basic layout of what it might look like, depending on based off one of the designs. And on the right is a sketch by Victor of P&H, who made just a simple idea of how it could work, depending on, obviously, mechanical teams and how that design ends up being done. And then talking about two robots, it'll be very similar code across both of them. They both have to move. They both have to see the environment, detect obstacles, traverse. The idea would be that both robots will have their own computers, and they will be able to communicate between each other to talk about, basically have one big state machine that would have separate branches for each one. And then when the traversal robot comes back and is ready for it to communicate, it would communicate to the big robot that it's ready for it to stop mining, transfer, and then do the transfer. And there would be an able tag on the big robot to actually align properly and make sure that everything would be properly set up. We do not expect that this will be a major lift from in terms of coding time and resources, as it will be very similar code across both of them. And we already have plans to change what would need to be changed. That is it. Any questions? Peter.
So this year, there's, as you mentioned, a big focus is on we have to sort of retraverse the same path over and over again. Last year, there were some problems with the system where going over, we would mess up the ground a little bit, and then that would be detected as new obstacles and would mess up the path. Is that something you plan to try to tackle with your revamped obstacle detection, or are you going to be trying to implement sort of like we've been here, we know it's safe, don't evaluate obstacles in that system?
So the main thing that caused that deformation was taking a lot of point turns. So actually the way that would get solved is from a path planning standpoint and like a cost maps setting. So essentially currently the way that we plan paths, if I kind of go back to that, you can see how it kind of takes a really tight kind of to the high cost region, a really tight path. And this creates a lot of unnecessary turns. So we're kind of hoping to move to a path planning scheme and a cost-based path planning scheme that really kind of minimizes the number of turns we make in terms of a deformation and a time kind of perspective. So that should reduce the amount of point turns we make, and so the amount of deformation we take. But in addition to that, we are also looking into more path following things. So path point to point, that does a lot of point turns, which we did find deform the environment a little bit. We're hoping that if like wheels allowing and drive system allowing, if we're able to do kind of a more spline-based system, kind of more curves, then we could have less deformation of the ground itself and have more consistent traverses.
I mean, that being said, we're looking at different obstacle detections, and we're definitely going to have some obstacle detections that we're going to try and tune so it doesn't detect our craters that we're but that'll definitely be dependent on if that ends up being possible based off of what they have had as rocks in the past not being very big obstacles and us creating bigger obstacles ourselves. So it depends, but hopefully through a combination of all that, we won't detect any obstacles that aren't true.
Yeah, so is the 2-box idea purely for organizational reasons?
Yes.
Because our current sponsor, ProtoCase, they fund 1 box, and we can always just enlarge the dimensions of 1 box. And kind of building off of that, is the separate battery also just for the wired organization of having 2 boxes, or is it actually a power need for the smaller box?
So, in terms of the enlarging the box, it was also a thing of if mechanical teams need that flexibility in where they want. I know that where the PNH box is right now, it was causing some issues with like excavation, would deposit onto it, and if they wanted to like reduce that angle significantly, they might start hitting it. So it was the thing of if we can make it a bit smaller and put it in some other locations, that would definitely help with that. I know that we also have sponsorship from Send Could Send, who could also make a similar box. That would also help with that. And then, yeah, sorry.
No, yeah.
Okay, and then power-wise, it would definitely be because of the power usage. Last year, our computer was using about 15 watts, and this year we're looking at 60-watt models. So it is significantly increased power, and that would eat into our power consumption, which will decrease our score. So, and we have the option of having a separate battery, so why not use it? It'll be better for score-wise.
The original estimate was like a 5 kilogram like PNH system.
Yes.
Probably be awarded, maybe even significantly heavier if we did a 2-box.
Uh,
From my understanding, we do need 2 batteries anyways, even if we were to ship in a 1 box, or just an upgraded battery.
You'd have to have separate batteries just because of one will have to go through the e-stop and power meter, because that is the main robot battery, and then the laptop computer battery would not. The ones that I was looking at were about like half a kilo, so in terms of battery weight, so.
And how much more advanced, like, do you think the smaller robots PNH box would be like the same needs and complexity as the large robots?
I do not think so. I think that we'll probably just have a similar to what we had this year at Jetson or Nano on the smaller robot, and yeah, definitely less cameras and stuff on it. Alex.
On this topic of sensors, the mini robot, what sensors do you anticipate needing on the little robot?
We'll definitely need some form of cameras on the mini robot. We'll probably need, if we are looking at obstacle detection, we're probably gonna have at least a LiDAR on it so that we can have better obstacle detection, since that was the main issue that we had last year. And then that would be probably the majority, that would be probably it for, unless there's like current sense or anything that needs for the linear actuators or motors that are being used. That is not something that I know off the top of my head. And then on the big robot would have the bigger compute, and it would have some cameras on it as well. Emily.
So there's an overall size constraint for the total size of PNH boxes can be. Is there concern with having 2 boxes and a tiny robot, or?
There's a size, what do you mean by that?
Like there's an overall size that all the PNH, like volume, all the PNH boxes can add up to.
Set by whom? I have not seen that before, and if that is true, I will look into that
I will
more.
find the section and send it.
Yes, please do. You had a question.
For the multiple robots and the sensors on each of them, could it be, I don't know, I feel like it might be pushing to the bandwidth limit, but could it be possible that the 2 could work simultaneously to create like a single map of the obstacles?
Yeah, so that is the current plan. Is we have the bandwidth limit is actually only between all of the robots and mission control. So between the robots themselves, they can communicate as much as they want. So the plan would be to have all frequent communication between the 2 and them to build a combined map so that they can both know where each other are and stuff like that. Isaac.
So So with the last year, we switched at the last moment to aligning to that with impact of the berm, right?
Yes.
Because the main difference was that our site was drifting and the alignment we needed, we weren't able to get just from a site. So now, especially with having to traverse back and forth, do you have plans for tackling that or addressing the slam drift besides the map code update? Which I've not been able to fully.
Yeah, so there's a kind of a multi-pronged approach to that. So first and foremost, as you're aware, last year we kind of implemented just the odometry feature and not really like the map correction feature. So we're hoping that to first test that on our new system, see how much accuracy we can get, especially over time, and how much the drift accumulates. But in addition, we are also going to be doing some fusion techniques. When we get the LiDAR and the depth cameras, we're hoping to fuse that input a little bit so that we have more accurate inputs to give to SLAM, which might help a little bit.
We're also looking at April tags and seeing if we can, we're going to do some more testing on how far away we can detect them from, depending on resolution and stuff. So if we can have April tags in our starting zone that we can see from further away, that we can then use to relocalize and make sure that we're staying at about the same spot. Will.
In terms of path following, I know you created path as you're driving. Was the plan to create a new path every time you traverse?
So the way that the path planning works is it's essentially just constantly creating a new path because the map keeps updating. Every time that there's a new map update, it generates a new path because it needs to integrate that new information into it. Sorry, is your question kind of?
This is kind of in relation with drivetrain, but if we're using the treads on the mini robot, which doesn't cause much deformation to the field, would it be quicker to breadcrumb our first traversal and then just follow the breadcrumb for the entire run?
Ooh, that one's interesting. So you're kind of saying like,
say we just map once and we just breadcrumb our first traversal and we just follow that existing path.
Yeah, actually, that was something that we were considering. So last year our kind of issue that happened when we got stuck in the same place when we were turning back and forth a lot, our indecision, it kept generating new obstacles.
Yeah.
So now, I mean, after we do our first plan, we're hoping that we can keep that cost map consistent because it's kind of assumed that when we do like the full plan with excavation going to excavation, the deposition robot going to deposition, we map the entire field and all the obstacles at the beginning of the map before we introduce any errors for deformation. So that was something that we were planning.
I was just thinking just less deformation from hopefully the treads. Maybe if you hit like correct me if I'm incorrect, but I think that may be able to like allow us to use that if it's quick drive.
Yeah, I mean, if you're talking about like manually driving it over one time,
no,
just
we
follow that path.
We only use the path following the creation and mapping the entire field.
Yeah. The path planning isn't particularly like long. It's a pretty quick process, so we're not too concerned about doing it repetitively. Yeah, that's basically.
You guys mentioned using machine learning is to like help with like detection. So I know during comp at one point it just like couldn't provide the path even though there like was one. It just was like almost like too smart for its own good. You guys had to turn on its sensitivity a little bit. Then that obviously causes other issues. Do you think that machine learning will help with that, or do you think it'll become like too smart and I'll see like a dent in the red alert and be like, oh no, greater, and then blocks every path?
Yeah, no, absolutely. So what kind of an overview of what happened at KSC during that first run. So we had our depth cameras set to scan a certain distance. What ended up happening is it detected an artifact of the bar that was above the ground, and it noticed that as an obstacle, which is why we reduced the scanning radius. So the idea here is that instead of going purely based off point cloud characteristics, which we were doing at competition, the idea is to train models on the image data because you can visually tell like what the difference is between kind of a structure that's above the ground versus a rock that's embedded in the lunar regolith. So we're hoping that does do a better job of classification.
And another thing that we're doing to help with that is that previously what we did is that we would only follow a path if it never touched an obstacle. If it had no point, like it never intersected an obstacle, and we're changing that so that it intersects the least number of obstacles and the least cost total. So like it will find a path and it will find the best possible path, and maybe that path isn't optimal, but it is still the best possible path.
Okay, and then I was talking a the robot, just bandwidth use?
Yes, so bandwidth uses between the robots and mission control.
Yeah.
And our current plan as of now is that right now, using situational awareness cameras that KSC provides us is 15 points, potentially. And we are thinking that is a worthwhile trade-off to have that extra view. So we are thinking that we will use that just to make sure, so we can prevent what happened in KSC Run 2, where we didn't know what was happening until it was too late. And we didn't want to turn on that camera because we would lose so many points.
15 points per full cycle.
Yes.
In the case of the path planner essentially going, like swapping in really different directions multiple times and causing the robot to essentially skip in place, would it be, I'm not sure if this would be any good of an idea at all. Would it be possible to essentially create like a minimum commitment time where it follows that plan for like 2 seconds, I don't know, and then it follows the new plan that's come up by them? Or would that be not the risk?
Yeah, so that was actually one of the solutions that we had in season last year was to, if we didn't move, if we just stayed in the same rough spot for a certain amount of time, we would stop planning and just keep okay, we have to follow this path because we haven't moved in a significant amount in the last 10 seconds. And it did work in some situations, but it wasn't perfect. And we definitely want a more robust solution that doesn't just have us. But also, if we just don't keep planning, we might see a new obstacle and we don't take that into account. So, Alex?
Yeah, on the little thing. So you mentioned peer pursuit and different path followers. Last year we tried peer pursuit, and then we had issues with tighter turns that we often require. Do you anticipate that still being an issue this year, or how do you, if not, how do you anticipate solving it?
So that one still has a little bit of work that we need to do into it. We still need to research that a little bit more. But essentially, the idea is, I think with Pure Pursuit, we were a little bit limited into how tight of turns we were able to make. So if we can kind of find a value and tune a little bit, and then kind of test that, but obviously it would require quite a bit of testing. We can't be certain about it until we kind of go out to the sand pits.
Yeah, I mean, last year we did basically no testing on it because point to point it worked pretty well. And if we can do more testing and do more tuning and it works better, that would be great. And if not, we have point to point.
And also about the sensors we have. You mentioned using a 3D LiDAR. What is the advantage of using a 3D LiDAR over one or multiple depth cameras?
So the way that 3D LiDARs work is that they are measuring the speed of light between the amount of time it takes for light to bounce off an object and return back to the camera, which is a much more precise method than depth cameras, which work by identifying the same pixels across 2 different cameras and determining how far it is based on parallax effect, which it can be, depth cameras are much more buggy in terms of certain, if there's a bright light, we'll just think that's infinitely far away, or it can have big issues. That'll be more accurate, and also it'll have a much wider range of view, which will allow us to see to the side much more, because last year we could only really see in front of us, which then if we're turning to the right, we can't see what's on the right, which is bad because we then turned into the rock and then it was too close for us to detect it.
Also, kind of something in addition to that, so the LiDAR, as Ankur mentioned, is going to be more accurate. It also sees a lot farther, so we can we can plan kind of a better long horizon path from the get-go. For example, second KSC run, Infamous, we kind of planned really close to the rocks, because we just weren't aware of what was beyond the area that we were planning, and it wanted to kind of scan what was known. So if we have kind of a longer horizon of where we're planning to, that could help inform a better path.
Really quick robot question. How would they traverse? Would it just be one goes and the other follows? And then would they ever just recognize each other's rocks and start acting weird towards each other?
Yeah, so we have a protocol for that we've kind of that we're still conceptualizing. We're still kind of working on that, but the overall idea is that, especially based on current discussion on the true robot idea, you have one excavator that just sits in the excavation zone, just constantly excavating. But it would have an April tag on it for localization. So essentially, it would keep excavating, and then when deposition's back from its deposition cycle, it would line up using that April tag, collect that. Collect the regolith collected, and then move over and deposit, and then just repeat that.
Would you have one do autonomous traversal, and then the excavator first, and then it'll sit there, and then the deposition, and does
The excavation zone is inside the starting zone. So no. Yeah, only the deposition robot would actually end up traversing across. Any other questions?
In regards to the LiDAR, those typically, the way that I understand they work is they have a rotating body that is what's actually shooting out the lasers to actually generate their white power. Are you concerned about dust obscuring those? Because I would imagine that those require a higher degree of heat than our depth cameras would. And are those sort of mechanisms entirely sealed in a container to prevent dust from getting into them?
Yeah, so I mean, that is something that we have to be concerned about. I haven't checked, I haven't done too much research into if they are like rated for dust protection or not. I'm not entirely sure. This is the model on the top right. It basically, I know that teams have used LiDARs previously. It's not unheard of. It may require us to put like brushes on it or something. We might have to like enclose the bottom of it or put like a glass thing on top, and that might work. We'll have to determine that if we get it, and if we can find specs online for what it's rated for. But it's definitely something that we're looking into.
Any other questions?
That was it.
I guess this is more one question, but not really. Ideally, if you just had a limited sensor bandwidth, how many cameras or sensors would you have on the robot to try and get this path prediction kind of thing as good as possible?
I mean, I think that having enough that you can see in both directions, like as you can see, like the right image here, having ones that you can see in multiple directions in front of you, such that you can have, like, you can see your sides better and you can see where you're turning and where you're going, would definitely be very useful. And also, if we could have that on the back as well, that would be great too. If we end up moving backwards at any point, I imagine if we end up with 2-robot design, it would be significantly less important for the main robot to have any like major sensors. It just needs a camera or two to be able to detect some obstacles that may be in the excavation zone, and then also detect where it is position-wise. The smaller robot that's traversing might not ever need to move backwards too much, so it could also not require back cameras, but definitely a couple cameras in front to determine how to move best is definitely required. I think that's it, so we'll turn it over to P&H.
Hello, my name is Victor Merz, and I am the team lead for Power and Hardware this year. So I'd like to start off with just a general system architecture of the Power and Hardware. This isn't accommodating of potential that maybe we have 2 boxes on the main robot. This is just generally how it will flow, regardless of what box things are in. So it's very, very basic system architecture. We intend to have 3 voltage. We have 48 volts, which is associated with the motor. We have 24 volts, which is associated with the linear actuators, saber tooth, and associated parts. And we have 12 volts associated with the Jetson. If we do use another battery, that'll obviously be another battery on its own. But if we cannot, for whatever reason, we can just use a step-down converter to 12 volts. And in general, it's pretty similar to what we had for last year's system architecture, just a few little changes here and there. For the mini-bot, it would also look very, very similar in system architecture, but I would like to point out here that there is no saber tooth or linear actuators. That's because we're not sure what deposition they want to use. If they need linear actuators, I'll have to change this. But for now, we're not planning on it, but I do intend this to change. This is just generally what the flow of the mini-bot might look like. So Power and Hardware is facing a lot of new challenges this year. This includes 2 robots. With the 2-robot idea, what would most likely happen is just duplication of our boards. In an ideal world, we'd have almost the exact same boards between each robot, with a few changes here and there, which I've spoken to the people making them about. And being able to use the same designs between them would be very, very big, because then our work would be doubled rather than quadrupled, because of course we also need backup boards. So in general, if we do 2 robots, we'd have to have at least 2 boxes. But now, because we'd like a separate box for software, we might have to accommodate for 3 boxes, which brings lots of challenges on its own, including CAD design, and then the limit on how big Power and Harbor boxes could be. So I'm still working out the logistics of that, but that is something we are trying to plan for and see if it's possible to do. And of course, the new Jetson is a potential hiccup in that it's very, very large to my knowledge. So a new box would be able to accommodate it, but again, that also brings challenges on its own. So that's something to take into account. And the first board we're working on is a battery protection circuit.
Hi, I'm Nicholas. I'm one of the ones responsible for the battery protection circuit. Basically, it's a testing board, because when we're testing before we go to competition, we might be testing it into the night, we might be leaving the robot on, and that might kill the battery. These batteries are very expensive. PCB is cheap, so we want to have this in our robot to make sure that we don't over discharge our battery and kill it. Now, we did implement this last year, and we had a couple issues with it. The first one was that the chip that we were using, the IC, had some bad thresholds, so it wouldn't really protect the battery, because once it actually triggers, the battery is already long dead, and we had to work around that in a scuff method. We've also had a problem where the IC had a weird backflow of power. Basically, it's not actually disconnecting the power for some reason, because it's feeding it through some really thin wires or whatever. And we also had a really jank method of connecting the battery to this board and then out to the robot. We're planning on using better connectors this time, and Linus can talk more about that.
Yeah, so for the plan for this year with this PCB, we are going to, instead of using some of these TI chips that have very low threshold values, where the battery would already be dead, we've come up with a couple of our own designs that would work instead. In addition, there has been interest to get a power meter, a logger basically, and so we can do that. We're going to have probably a second board in addition to this that is battery diagnostics, where we can connect to those cells. We can measure the total current draw of the robot, but then also measure the individual voltages of each cell using one of the fancy TI chips. And overall, it should give us kind of a good reading of our power usage over the course of an entire run. This could stay in the box and connected during the run, instead of where the second board would. This first board again would be taken out during the run, because we don't need battery protection during the run. So I think next slide, Teensy.
Hey guys, I'm Arish. Eve and I are working on the Teensy board along with some of the people in PNH. This is mostly the same, at least for the time being, since it's just all of our signal in and out. A lot of the stuff that software's either controlling or reading from is going through this board. Things like your motor controllers, your LED indicators, things like that. Like I said, a lot of it's going to be very similar, since it's really just handling everything else. So we're kind of waiting to see what everyone else needs and wants to be able to run, and what software needs to be able to see. As far as the 2-bot, mini-bot thing, the only main difference between the 2 boards will be the amount of power we're pulling out from the motors, depending on 48 versus 24 volt. Yeah, I think that's really everything. It's not a huge amount of overall happening for a Teensy.
Current sense. All right, current sense. So there will be current sense boards that measure current and send that info to the Teensy board. Different from last year. I mean, if you look at last year's schematic, you'll see there's one schematic, there's one board. There were multiple of them. They're all the same schematic. This year we'll have 2 different designs at least, one for measuring current going to the linear actuators and one for measuring all of the current coming from the battery. We'll need 2 different schematics just based on the amount of power.
And with that, for the battery specifically, we're going to need to find higher current Hall effect sensors due to it being so close proximity to that and just the increased demand overall, especially of having one in each box. But also, we're planning on using Wago connectors for our high current wires because like dripping solder onto those like frayed wires wasn't exactly the best idea. It's kind of jank. So the Wago connectors will make it a lot more streamlined and also secure. But that also means that we're likely going to have to increase the size of the board itself to fit the sheer size of attaching the terminal to the PCB. But other than that, yeah, that's pretty much it.
So there's quite a bit we're doing in box design, again, especially because we're having multiple robots and potentially multiple boxes for each robot. First being breakers. Breakers are included for many reasons, the main one being safety. So obviously breakers just make sure everything is electrically separated, prevents correct backflow, make sure that nothing propagates throughout the rest of the box if something goes wrong. So at the moment, we are still waiting to hear from other sub-teams about what components they'd like to use, so we know how to size our breakers properly, but we are using last year's data to see what should be implemented in our breakers, to see potentially what we can work with, even if we don't know exactly what they want at the moment, and also to get a better read on what it might look like in competition. So another big part this year is part research. So the main robot is actually going to be pretty similar to last year. So there's not that much part research to be done, except for the fact that if it is two boxes, we will need things like extra connectors. We'll need to figure out how to connect the two boxes and what the logistics of that look like. So that will require quite a bit of work. But the main thing is the mini bot. Now, most of what we intend to have in the mini bot, I believe, can run on 12 volts. So we're seeing if maybe we could run it off a 12 volt battery. And then if maybe just the motors are 24 volts, we can just have something step up the current, the voltage there, excuse me. And if that's the case, then that's great. Or we can also just run it off a 20 volt battery as well, and then just step down to 12 volts too. It really can go either way, but it would be nice if we could just run it off a 12 volt battery. But it will be generally similar to the main robot, except like I said, depending on what deposition decides to do, we may or may not have linear actuators or a saber tooth, and then small things like that. And it also depending on what software we'd like to do between the two boxes, what might be different there. And that is, I think, it. Yeah, are there any questions?
Yeah, so you mentioned having breakers for certain motors. Then a lot of motors and motor controllers we're looking at already have built-in overcurrent, overvoltage, over all of the fun stuff protection. Do you think the breakers still have what do you think the voltage breakers would be in that case? And are you worried about the breakers tripping too early? If the motor says, hey, I can still give you more, but the breaker says, no, I'm going to turn you off right now because I think that you're drawing too much power. Well, the motor still takes time.
Yeah, I believe we've had issues with that in the past where they trip too early, and then that obviously messes up the run. Part of the reason why I put what we should connect and why I said we're looking at previous data is to see if there is a case where we don't need breakers, such as for the motors maybe, if it is proven to be safe, we might see if we might not need them for that specific component, but it is good to size them for everything, at least right now, especially in the early stages, to make sure that we have a contingency plan for everything, just in case we do need to add safety to every single component. I would rather every single component that needs breakers be safe rather than kind of throw things around willy-nilly and hope that nothing shorts.
I noticed that you had a team developing the power distribution board again after it was a senior design last year. Is there like any hope for that like actually being implemented in the robot? Obviously not. Not that like we don't believe in them, it's just really last minute. I was just wondering your thoughts on that.
Yeah, frankly, I can't see it being implemented this year. If it is, that's great, you know. However, the reason it is a research project is because something as big as a power distribution board, which handles multiple buck boost, buck and boost converters, is a very big project. So I honestly can't expect someone to get that done within a span of a year, especially with not only constructing and designing, also testing. That's going to take a while too. So that's part of the reason why I believe it's a research project, so that they do have the extra time to maybe take an entire year just to design and then to construct, and then take extra time to test to make sure that it actually works. Because especially again with components like buck boost converters, there's a lot that can happen and a lot that can go wrong. So it's important to test every single aspect of it because they can be very volatile if the smallest thing is wrong with them.
Okay, thank you.
Thank you guys. Okay, so for systems, we don't have that much to go over, but something that we developed and are reusing from last year is our integration plan and risk assessment. This is pretty much just a document to help us determine what our key integration threats are and how we can avoid those. So they're more organizational and high level for the system. So things like miscommunication, unclear documentation, misinterpreting the rule book, or forgetting deadlines. These are really important things that we can't do and will have very bad consequences, but fortunately, there are easy ways that we can help mitigate those. For example, in this document, we have a lot of mitigation strategies for this. Systems will also be regularly conducting integration and risk analysis reports. This is going to be a little more informal, just so systems can document and stay aware of potential issues, so we can ensure that those don't happen or nothing bad happens because of them. Usually the subteams do a really good job at identifying the integration threats between themselves. So systems will mostly just be facilitating and ensuring that subteams are communicating about these issues and taking care of them.
Okay, so for PDR, it's going to be November 15th. We don't really know actually we do. It's going to be right here. And so this will just be to make sure that each of the subteams have their components integrating well with each other, and to ensure that everything is meeting the system requirements and it's acceptable in terms of schedules and cost. And so here are some of the review trackers. So on the left, we have our review package, and it shows all of the items that we have to get done. So budget funding report, for example, and the responsible party is the business team. And then entrance criteria, pretty much the same exact thing. We have a lot of things that we need to get done, and who is going to take care of that. You can find these in the drive, review gates, review trackers. And so here are some checklist items to get done before PDR. So each of the sub-teams pretty much continue what you're doing now. So it's a lot of trade studies, DFMEAs, and PDR slides as well. And systems, we're obviously going to be working on PDR and ConOps and the review package and PDR slides and other stuff as well. President, pretty much the same as he's been doing, I guess. So team schedule and PDR slides. And yeah, and this can be found in the Google Drive for the templates and resources.
Let's go into a little bit more detail about one of the things all the engineering subteams have to have done for PDR is the DFMEAs, which is the Design Failure Mode Effects Analysis. This is the safety document that all the subteams should be filling out. Although it is due by PDR and you're going to be presenting it there, we hope that you can get it done as soon as possible, because it is a tool for you guys to help make sure you are being safe, although we are still in the design phase. You can find it in the systems folder within the template subfolder in the drive. You can pretty much reuse a lot of the stuff you have from previous years, but updating it and adding anything new that you think of. Within the template, there are lots of instructions and information on how to fill out the table. So hopefully you won't get lost filling it out. Most of you guys have seen these before. But if you do have any questions, please feel free to reach out to Systems, Radon, or I, and we can help solve any issues you may have. And that is all for Systems. We'll hand it off to Business and the treasurers now.
You have a question?
Question, sorry.
With this mini bot discussion, how is Systems going to work in ensuring that that is all integrated properly? Or what is Systems' plan for the two robot solution at the moment?
Yeah, so we're gonna help work with Andrew, and Alex is a big proponent of this. So we're gonna help work with them to make sure that we are documenting all of the things all of the integration things we need to keep in mind, and just make sure on paper that we understand how this is gonna work. The engineering sub teams are gonna do a lot of the brainstorming for how to do that integration, obviously, but we're gonna be there to help make sure that everything is taken care of and we're documenting it to make sure we're not missing any steps. Okay, thank you.
Since business is walking up, we have been in a pretty good spot thanks to the last leadership team funding wise. The main thing that Erin will talk a little bit more about grants, but one of the big things we did over the summer was we've streamlined the process for the bill of materials. We have consolidated it into one EBOM and have the part order form fill in to the EBOM so that we don't need to fill out 4 different forms. Learned that. Yeah, same thing with reimbursements. We've kind of tried to streamline that process a little bit as well. And we are trying to improve the documentation side of business. Oh, yeah. We're trying to improve the documentation side of the finances a little bit more, keep track of what emails we've sent to which companies, how much we've gotten, just for the sake of the next leadership team to be able to have more of something to look at next year.
Yeah. In terms of like where we get our money, most of our money so far has come from grants. So SVAB and Pepsi have done a lot for us, but we also have a really long list of corporate sponsors that we are in the process of reaching out to. So hopefully with a combination of those and internal engineering departments as well, we've been in the process of communicating with them. So hopefully with all of those, we have enough funds to not only cover everything that we need to for this year, but also provide a good kind of foundation for next year's leadership as well.
And as business operations lead, I've been working on the outreach side of the social media, and then also informing people to have our social media be a source of information for all of our team members. Also, I am working on some of the corporate sponsorship proposals and working on our polos. We should have them by the end of October. Thank you.
All right, the long-awaited concluding remarks. What an SDR. That was, for reference, last year's SDR was 2 hours and 20 minutes. Drivetrain alone, I think, went 90 minutes this year, so almost there. But I think that really speaks to how much we've grown and how much work we've been able to do in such a short amount of time. So I'm really proud of all the work the sub-teams have put into making today such a great presentation, such a great SDR. I believe all the sub-teams are in a fantastic spot and looking forward to the future. I think we're gonna have a really strong robot system this year. So looking at some of the upcoming events, nothing too crazy. We have budgets due for the sub-team leads at the end of the month, so make sure you get those in. Also, next weekend, the nominees for the United Kingdom trip will be traveling abroad. So we'll be taking Albie during that time, last year's robot. Then sometime mid-October, we'll be having that Girl Scout Day and Produce Space Day. So if you haven't signed up for those, I'd recommend doing so. If you want to maintain that active membership, participate in at least one volunteering event. End of October is our tentative date for team photos. Hopefully by then we'll have distributed our polos. And then in November, we'll have Produce Space Day, another opportunity to get that active membership. And then in mid-November, we'll have our PDR, which is the next time we'll reconvene. I'd like to thank all of you for being here today and presenting. I know it was a little longer than we had initially planned. I'd like to thank our alumni. I think this time just one alumni who showed up in person, so thank you for being here today, as well as for everyone who turned in on the live stream. I know we've had a couple alumni and industry professionals on there. We appreciate you being here and giving your input. I know our systems teams and some of our other members in the crowd have taken notes. Those will be in the drive for us to reference moving forward. If you have any other questions, I direct you to talk to your sub-team leads or the respective parties after this meeting. But with that, I'd like to conclude today's SDR. Thank you all for coming and have a nice day.